Okay, not getting. Okay, let me.
Yes, now
Now it
it's coming.
Oh,
is
now
coming.
it is coming.
Yeah, it's
Oh,
okay
so
now.
could you see the slides?
Yeah, now it is coming.
Ah,
Yeah,
okay,
yeah.
okay. Yeah,
Yeah.
so before I start, let me thank uh,
Yes.
the
Yes.
organizers, and special thanks to Malay for this opportunity. And this is a recent work with my colleagues in IIT Kanpur, Soumitra Ghara and MT Ramiz Reza. So this is about an old problem which I asked around when I was a PhD student around 2006, and so the problem is open as such, but we are going to discuss a couple of cases in which the answer can be given affirmatively. Okay. And I will not go through the abstract. I kept the slides as minimum as possible, and I'll try to convey the essential ideas uh, involved in this problem and possibly some partial solutions.
Somil,
Yeah.
sorry to disturb
Huh.
you. Could you please enter into the full screen mode?
Oh, yeah, sure, sure.
Yeah,
Ha.
thank you.
Yeah.
Thank you.
Oh, yeah. Okay. So, so the setup is obviously we need Hilbert spaces. So D and E these are complex separable Hilbert spaces. One can think of CN uh, finite dimensional spaces or little L2. That would be sufficient for this talk. And this B of D is the collection of bounded linear transformations from D into E, and then we define the Schur class. So Schur class is nothing but the unit ball of bounded holomorphic functions in the vector valued sense. So these are functions from unit disk into this space of linear transformations, and we demand that the function must be holomorphic and its sup norm should be at most 1. Okay. So this is the unit ball of the H infinity. H infinity is the usual symbol for bounded holomorphic functions. And the basic reference for this Schur class is a recent monograph by Agler, McCarthy, and Young. So it is published in 2020. And I recommend this book for the beginners who are interested in function analysis. Okay, so excellent book. So they have so the one of the features of this book is you can implement methods from operator theory or function analysis to prove certain results in complex analysis. Okay, and this is very recent, so I think uh, this uh, uh, this has many developments, recent developments and old developments as well. Okay, so let me now move to the next slide. Okay, now we define so-called D branches Roanoke space. It's a object or it's a space lying there for more than 50 years, and the old reference is due to Donald Sarason, 1994, and this space was it. This space also is related to the work of D branches, the famous guy who settled Weber-Buck conjecture, and this is a space which is reproducing kind of Hilbert space. So it's a Hilbert space with the property that if you look at the map f going to f of z, then this defines the bounded linear functional. Okay, and it has a reproducing kernel kb zw given by this formula, where this b symbol which we have taken from the Schur class appears, and you see that because b is in the unit ball of the H infinity, this is positive definite. I minus bz bw star is bigger than equal to 0 in the sense of kernel. And then you are dividing by multiplying by 1 upon 1 minus zw bar, which is the famous Cauchy kernel. Okay. And this is a reproducing kernel in the sense that if you look at this as a function of z and fix w, and you take the inner product of any element in the Hilbert space with this vector k dot w, then you get the value of f at w. So the value of f at w is reproduced by this kernel, and that is why it is called a reproducing kernel. And this reproducing kernel appears in various contexts. So uh, this there are some technical conditions definitions, like you say that the kernel is normalized if kbz0 is the identity operator. See, because here we are talking about the operator valued kernel, so here you need identity. In case e is just one dimensional, you get just constant 1. And this is equivalent to the condition that b of 0 is 0. So the classical deep range spaces corresponds to the case when D and E, these are just one-dimensional Hilbert spaces, namely the complex plane. Okay. And you'll get lot about the classical deep range spaces in this monograph of Sarasan. For higher rank or infinite rank deep range spaces, this study has been started recently in 19 with 2-3 papers. One 19 Aleman Malman, then second due to Richter, and then there are various papers in this last 2-3 years. Okay, so let me explain you a little bit about the classical deep range spaces. So if you take the symbol to be a bounded Borel measurable function, then you can define the Toeplitz operator. And if B is coming from the unit ball of the H infinity, then one can compute that TB bar is TB star, which is at most, which is less than or equal to identity. Or you can say that I minus TB star is a positive operator. So one can define the square root. Once it is a positive operator, you can define the square root, and you can form a new space, which is the range space of this square root, and you impose the appropriate norm. Okay, now what it has to do with the de Branch space? So it turns out that the de Branch space, which I have defined in the last slide, is same as this range space with this norm. Okay. And however, one needs to be careful because the range is not the de Branch space. Okay, so the range of the square root, and that is why the range of I minus TB star is dense in HB, and you can compute the norm. Okay, but if you ask to compute the norm of arbitrary element in the space, it's a difficult proposition. Okay, so we do not have formula for the arbitrary element, but we have formula for a dense subspace, and that is why the study of de Branch space is bit uh, uh, critical. It's you need to because you do not have formula. So see, this is different from the classical spaces, namely Hardy space, Dirichlet space, Berman space, and like that. Okay, and uh, so here is a known celebrated result due to Liu and Rudin, Walter Rudin, proved in 1958. So it says that Z is a multiplier if and only B is a non-extreme point of the unit ball. Okay, so non-extreme point means it doesn't lie on a line segment. Okay, roughly, and so this is a, so you can see that Z is a multiplier. This means that if you look at the operator of multiplication by Z, it's a bounded linear operator. Okay, so this is a operator theoretic statement, and you are characterizing it in terms of a statement from function theory, namely it is a non-extreme point of the unit ball of the bounded holomorphic functions. So so there are couple of volumes uh, on classical de Branch spaces. So due to Fricken and Masharagi, so they are quite uh, large in size. So this is what I've just cited volume 2. Volume 1 is basic material, and volume 2 is on these spaces. So they both are of size 600 pages, 6 to 700 pages. But this is if you want to, if you are interested in these spaces, this is a this is a necessary reference. Okay. So let me now explain you finite rank de-branch spaces so that we can formulate the problem, Cauchy-Dual subnormative problem, in this setup. So here you can allow D and E to be the Hilbert spaces. Only thing is that we impose some condition, namely we look at the infimum or the dimension of D tilde for which HB is HB tilde. Okay, and B tilde is coming from, it's a sure function from D tilde into E. And you take the infimum. Okay, so you expect that this K is finite, and if K is finite, then you call the D branch space to be of finite rank, and the rank is precisely K. And one of the examples is that if you take D to be Ck and E to be C, then the rank of HB is precisely K. Okay. So now we'll focus on finite rank D-branch spaces, and one may think that the study of classical and finite rank both are just uh, the, 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 the argument or the methods involved should be similar, but there are some surprises. Okay, so like this, firstly, this, if you look at the characterization of multipliers, z is a multiplier, so there now this here there is no counterpart of non-extremum part. Okay, so we say that B is a non-extremum point of the unit ball of H infinity. You do not have, but you have something, so namely this condition integral over the circle of log of 1 minus now this sum modulus bj tilde square. So bj tilde, these are the boundary values, non-tangential boundary values of B at zeta. And so this condition in if you take K equal to 1, you get you deduce the result of Liu and Rudin. Okay. However, uh, uh, for higher K, one doesn't know what do you mean by non-extremum point here, because see, now you have to, because in classical there is only single B, here now there is a tuple. Okay, so you have to all the time relate everything to the tuple, and you'll see that there are plenty of surprises in the classical in non-classical de-branch spaces. So let me now, yeah, so this is a recent result uh, published in 2020 in Advances in Maths. So it provides a model formula, and it says that essentially you take any bounded linear operator, you impose a little bit of conditions like left invertibility, and the it is norm increasing in the sense that norm of ZF is bigger than equal to norm F. Okay, or norm of TF, if you are talking about the arbitrary operator, bounded linear operator T, the norm of TF bigger than to norm T. Okay, if you have these two conditions, and okay, there is one more condition, namely analytic, which is also, it essentially says that the intersection of the hyper intersection of all powers of ranges is trivial. So we have these three conditions: analytic, norm increasing implies left invertible, and then the operator is necessarily unitarily equivalent to multiplication by z on some vector valued D branch space. Okay, so you can find some symbol Bt, which is a Schur class function, such that h of Bt, the multiplication by z on h of Bt is unitarily equivalent to T. Okay. So this says that the study of any uh, norm increasing operator which is analytic, the study of such operators is reduced to the study of D branch spaces or multiplication by Z on the D branch spaces. Okay. So this model theorem is the starting point of uh, Cauchy-Dual subnormative problem. Okay. Starting point in the sense, if you want to formulate Cauchy-Dual subnormative problem in this setup, then this is the starting point. Now, this result can be generalized from a can be obtained from a result of Shimori. So let me just wait, because to state the Cauchy-Dual subnormative problem, you need some more definitions from this paper of Shimorin, published in Creley Journal in 2001. So see this, if you have heard about the Moore-Penrose inverse, then so many times the operator or the matrix is not invertible, but it has some inverse which is a pseudo inverse. So, and that inverse is helpful in solving system of equations or in solving uh, eigenvalue problem. So here also, for bounded linear operator, if it is left invertible but it is not invertible, okay, then you can introduce a inverse which is not the full inverse. It is called the Cauchy dual, and so it's given by t into t star t inverse. And if you take the adjoint of this Cauchy dual, then you will see that it is the left inverse of t. So, and another feature of this Cauchy dual is that if you take, because t prime is also left invertible, if you take the dual of t, means t prime of prime of t prime, then you get t back. Okay, so in that sense it is dual, and this, yeah, this is what I said, t prime prime is t, and this Cauchy dual has been very influential in various results in function theory and operator theory. Okay, so uh, there are many uh, papers on this aspect. So let me introduce a couple of more definitions, namely, uh, we call a boundary linear operator a two isometry. So you recall, isometry means T star T is identity, and two isometry means I minus 2 T star T plus T star square T square equal to 0. Okay, now you may wonder, you may find this definition artificial, but you will see that if you look at the function n going to T star n Tn, okay, you compute all order moments, T star T, T star square, T star cube, T cube. So you will see that if T is two isometry, then this function T star n Tn, a function of n, it's a linear polynomial. And in case of isometry, it's a constant polynomial, because T star T is identity is just constant polynomial. Because T star T identity, T star n Tn is also identity. So it's a constant polynomial. So for two isometry, the moment is a degree 1 polynomial. And you can define M isometry also. You expect that the moment, sequence of moment, is n minus 1 degree polynomial, and so on. Okay. So for our for the Cauchy-Dual subnormative problem, we just need two isometry, and that is what we stated. So we need another definition which is called subnormal. So namely, operator is subnormal if it has a normal extension. So given suppose you have operator T on H, so you can find some bigger space which is bigger than H, and there is an operator N acting on this bigger space. This N is normal, and when you restrict N to H, you get T back. So with this definition, we can state the Cauchy-Dual subnormative problem. A couple of facts just before that: every isometry is two isometry expected, and isometry is subnormal, but two isometry is subnormal if and only if it is an isometry. So these are elementary observations, but nevertheless they give example of subnormal operators. Okay, now we'll state the. By the way, how much time do I have? You can just. Yeah, I hope I have. Okay, okay, fine, fine. So the so this is the first version of the Cauchy-Dual subnormative problem. Now the problem is that if you start with a multiplication by z on d branches space, and assume that this multiplication by z is a two isometry, when the Cauchy-Dual is subnormal. Okay. Now you may wonder what it has to do with is why this question is important. Okay. So it has roots the in harmonic analysis on semi-groups, namely, uh, if you take the operator to be very simple, namely it is weighted shift. Okay, what do you mean by weighted shift? You take an orthogonal basis and send En to some weight Wn times En plus 1. So it's a shift operator with some weights. Okay, you can think of as a matrix, and the lower diagonal means just below the diagonal there is a so you put the entries W0, W1, W2, and so on. Okay, and all other entries are 0. Okay, now this is weighted shift operator, and you compute the co-schedule of the weighted shift. Then you will see that the weights of weighted shift, uh, if they are Wn, then the weights of the co-schedule it is 1 over Wn. Okay, and so there is a you can see that the moments of uh, t, if it is beta n, then the moments of the co-schedule are 1 over beta n. Okay, so this is the property of weighted shift. Okay, now there are plenty of results, because 2 isometry, as I said, it is just linear polynomial. Okay, and one can show that if you take 1 upon a linear polynomial which is non-negative on close 0 infinity, then it it is a Hausdorff moment sequence, and Hausdorff moment sequence amounts to subnormality. So you'll find that this problem can be thought of as non-commutative analog of this fact. Okay, and this fact is attributed to various people, Schoenberg, Bernstein, so many people. Okay, so this fact has been in the literature for several decades, and this can be thought of as a non-commutative analog of that. And there are if the co-schedule subnormative problem has affirmative answer, then it has very interesting implications to the spectral theory and function theory as well. Okay, so we'll not get into those, but let me just tell you some developments. So in case of unilateral weighted shifts, Atole has solved this problem affirmatively. This is a 1996 paper in Proceedings of AMS. Okay, for the rank 1 case, namely T star T minus I, rank of this is 1. So it's a result of Kathleen Badia and Sushu in JMMA in 2019. Okay, and for operator weighted shifts, it's work with Anand, Yablonsky, and Stohel in JFA in 2019. And then, but all these are positive results. Okay, so in the same paper, uh, and then there is one more paper in Advances in Operator Theory. So we found counter examples to this problem. So counter examples in the sense that this, in general, the co-schedule for 2 isometry need not be subnormal. Okay. So these counter examples are based on weighted shifts on directed trees. Okay. So you need to implement methods from graph theory to produce these counter examples, and you can also do this using the theory of composition operators, weighted composition operators on discrete measure spaces. So okay, but still, this is not the end of the story. This all these examples. Okay, so I didn't write here, but all these examples, in all these examples, the rank of T star T minus I is infinite. Okay. So the rank 1 case is affirmative. Infinite rank, there are counter examples. Now the question is that what happens if the rank of T star T minus I is finite? Okay, and this is a curiosity. So we are going to address this problem. Till now we do not have any counter example, because we are going to produce some affirmative answers in the case of rank 2. So for that, we need to recall the theory of Dirichlet type spaces. So you start with the space of complex valued holomorphic functions. That's denoted by OD. Then dA is the area measure, and mu is a finite Borel measure concentrated on the unit circle, and this mu z is the Poisson integral. So it is the integral of 1 minus mod z, integral of the Poisson kernel, okay, with respect to mu. And then you form the space, those holomorphic function for which this integral, the basically uh, the norm of f prime with respect to the weighted area measure with weight being p mu z is finite, okay. And this is a semi norm. You can add the Hardy norm to make it a norm, and this is a reproducing kernel Hilbert space, and it turns out that every cyclic analytic two isometry is multiplication by z on some d mu. So you can find a major mu, and this is a result, old result of Richter, proved in published in Transactions of AMS in 1991. Now, with the help of this, you can reformulate Cauchy-Dual subnormative problem. Let's call it version 2. So classify all finite. So we are just now confining ourselves to cyclic. Okay. So classify all finite positive Borel measures. Because of this theorem, you can just ask what are all measures mu? Because you know that multiplication by z on d mu is 2 isometry. So for which the Cauchy-Dual mz prime is subnormal. Okay. So how the information, see, because we want now answer in terms of the measure, and the advantage is that you can use result from the theory of Dirichlet type spaces. So there are so there are, in fact there is a entire book on Dirichlet spaces, okay. So these are natural generalization of Dirichlet spaces, and there has been voluminous literature on these spaces. So as I said earlier, the counterexample as constructed in this is a cyclic two isometry for which range of t star t minus I is of infinite coordinate, infinite dimension. Okay. So we'll just now confine to the class of cyclic two isometries for which t star t minus I is of finite rank. Now all these two isometries can be classified in terms of the measures. Okay, how? So here is the statement. So you assume that t star t minus I is of rank k. Okay, then you can find points zeta 1, zeta 2, zeta k on the unit circle, and these are distinct points, and a positive number c1, c2, ck, so that this the model space d mu, the measure mu must be linear combination of Dirac delta measures. So it must be summation j from 1 to k cj delta zeta j. Okay. And the converse is also true. If you start with such measure, then the rank of t star t minus I is k. And this theorem allows you to reformulate Cauchy-Dual subnormative problem. We call it version 3. So classify k tuple zeta 1 to z, because now the information about the measure is now stored in the coefficient cj and the points zeta j. Okay. So classify k tuple zeta 1, zeta 2, zeta k of distinct points on circle, and k tuple c1, c2, ck of positive real numbers for which the Cauchy-Dual mz prime is a subnormal. Okay. And the okay, so now this is a technical result. I'll not get into this, but let me uh, first tell you what is the result we prove. Okay, and then I'll come. Okay, so this is the result. So for rank 2, if you take, because rank 2 means there are 2 points zeta 1, zeta 2, so that the measure is c1 delta zeta 1 plus C2 delta zeta 2. Okay. If you assume that the points 2, zeta 1, zeta 2, they are antipodal points, okay, then the answer is affirmative. However, we do not know what happens if they are not antipodal. In particular, suppose you take zeta 1 to be 1 and zeta 2 to be I, then we the methods or the method of proof uh, doesn't give any information. And how to proceed? So the idea is that we'll analyze, because see, this all this d mu, because multiplication by z on d mu is a cyclic two isometry, so two isometry. And the first model theorem we stated, it says that you can model this d mu as some d branch space, okay. So that d branch space will give you a symbol, and it turns out that that symbol is a rational function, and this p, so you'll find that the symbol is, because it's of rank 2, so it will be of the form b1 b2. Each b1 is a rational function, so there will be a numerator which is p1, and so we are going to analyze the this orthogonality condition related to p1 and p2, okay. And so here actually this j, I should have taken 2. I think there is yeah, means you have to just say that this holds. Okay, I am going to tell what is the general condition, okay. So this is the orthogonality condition, and this, what are alpha 1 alpha 2? They are precisely the roots of the numerator of the symbols, okay. So it turns out that all these symbols, their denominator are p1 p2, but numerator is same, okay. And these are the roots, and if you have this, if you get this orthogonality condition, then you can obtain the subnormality, okay. So now, to let me go to the last slide, okay. So you will find that this orthogonality condition is there, okay, implicitly. Namely, this is the term pj alpha summation j from 1 to k, pj alpha r, pj alpha t conjugate, and r should be not equal to t. So because sorry, means in general we allow all, but when we get orthogonality condition, then we allow r not equal to t, okay. That is why we are taking 1 2 2 1, okay. And the subnormality of the co-schedule of mz on the Dirichlet space, finite rank Dirichlet space, can be characterized as the positive semi-definiteness of this matrix. This is, you will see that this is an infinite matrix. Okay, this is a matrix, and then you are multiplying by some scalars, and then you are taking finite sum. Okay. So whenever you get the matrix to be positive semi-definite, okay, now if you have this orthogonality condition, then you will see that the terms corresponding to r not equal to 2 will vanish, and you are left only with r equal to 1 to k, r equal to t equal to 1 to k, and that can be seen to be a sum of positive definite matrices, which is also positive definite, and that gives the result. So there are some technical points involved, but I think there is no need to get into that. Yeah. So this is the, so these symbols look like pjz divided by product of z minus alpha j, and alpha j are the roots of the denominator, okay. And so however, the methods are insufficient once you move to higher ranks, namely rank 3 and so on, and rank 3 onwards. So we hope that we'll come to this problem in the future. Okay. So I think I'll stop here. Yeah. Thank you. Thank you very much.
Any question, please, from audience side? Well, just I want to know whether these results are applicable to multi-valued operator or not.
Uh, See, there are some results in for computing tuples also, but as such, these results because the notion of D-branch space for in several variables has not been formulated yet. So there are serious
Okay.
issues related to that. Yeah, yeah,
Okay, that means there is enough scope to
yeah, yeah, yeah. Certainly,
develop that
certainly. Yes,
area
yes, yes,
in
yes, 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 yes,
the
yes, yes,
multi-valued case or some other
yes, yes,
similar
yes,
cases.
yes.
Yeah. Uh, any other question, please? So let us give a big hand to Professor
Thank you, thank you.
Sameer Lakshman Chauhan for delivering a very nice and
Yeah,
illuminating talk
thank you.
over here. I again thank Professor
Yeah,
Chauhan.
yeah, yeah, yeah.
And from the society side, I also, on behalf of the society, I also thank Professor Chauhan.
Thank you, thank you.
Now over to Dr. Ghosh.
Yes,
He is
thank you very much.
announcing.
Yeah, is it coming? Yeah. So thank you very much, Professor Shom and Professor Chauhan also.
Thank you. Thank you.
And we are concluding this particular invited talk session. And now we are moving to the parallel sessions. As you have already seen, that we are having three sessions, 4A, 4B, and 4C. And I think if you follow the chat box, who are in
Yeah.
the 4A session, they will stay here. And 4B and 4C, this particular links are being provided. So please join accordingly. And after this particular parallel sessions, we will be again coming back to the main session where we are having the final talk. This is a Shahan Shaha Memorial Lecture provided by Professor Ruiz, and then it will be followed by the valedictory session. So thank you very much. Please join the parallel sessions accordingly. Thank you.
So this is the paper presentation session, and this session is 4A, and the name was proposed Professor Kalishankar Theory to chair this session. Due to some unavoidable circumstances, he could not join here. Uh, so in this circumstance, as a convener, I have to carry on the session. Uh, there are exactly 9 papers to be presented in this session, and I will mention the names: Anjuna Bhattacharya, Alauddin Dabadar, Swati Sharma, Mayank Pandey, Ali Ahmed Abdullah, Junaid Nisar, Argotanu Manna, Shapon Samanto, Abul Kalam Mondol. Professor Kalishankar Theory, are you here? Most probably no. He informed us about his inability. Okay, so if all are present here, we will start the session. So our first speaker is Anjana Bhattacharya. Are you here?
Yes.
So I would like to request you to present your paper.
Good evening to all of you. My topic is AFSWG applications. Outline.
Can you make it full screen?
Control F.
If you are using a laptop, you can put F5, or you can go to File. Here you view. You say at the left corner of your screen, top left corner, there is a view option. View. Yes.
And
Then full
full screen mode.
Right. This is.
Full screen mode.
Yes. Yes, it is perfect. Please
Thank you.
go ahead.
Thank you. In one of
It's coming probably. It is echoing.
In one of my paper, we have introduced FSWG closed set. Using this set as a basic tool, here we introduce FSWG closure operator. And using this closure operator, here we introduce new type of regular, normal, and compact spaces. Also, we introduced some functions like closed, open, continuous, irresolute, strongly continuous, weakly continuous functions. And then establish the connection between these functions, and also the application of these functions on the spaces are established here. First, you recall the following definition. A fuzzy set A is called fuzzy semi-open if A less than equal to closure interior A. The complement for the semi-open set is called fuzzy semi-closed. The smallest fuzzy semi-closed set containing a fuzzy set A is called fuzzy semi-closure of A, denoted by SCLA. Now we come to our main section. In this section, we first recall the definition of FSWG closed set. A fuzzy set A is called FSWG closed if closure interior A less than equal to U, whenever A less than equal to U, where U is fuzzy semi-open. The complement of FSWG closed set is called FSWG open set. We have an important remark that union and intersection of two FSWG closed sets may not be follow from these two examples. So we can conclude that the set of all FSWG open sets may not form a fuzzy topology. Now we come to our main section. We first define what is called FSWG closure and FSWG interior operator. For a fuzzy set A, FSWG closure A is the intersection of all FSWG closed sets containing a fuzzy set A. And FSWG interior A is the union of all FSWG open sets contained in A. So we have a remark that FSWG closure A for any fuzzy set A lies in between A and closure A. And if A is FSWG closed, then A equal to FSWG closure A. But in general, FSWG closure A is not FSWG closed. Similarly for open. Now it is an important theorem that for a fuzzy set A, if xt is a fuzzy point, xt belongs to FSWG closure if and only if every FSWG open Q neighborhood U of xt is Q coincident with A. This is the property of FSWG closure operator. It takes 0 to 0, 1 to 1. It is an increasing operator. It distributed over union, but not on intersection, and it is an idempotent operator. And this is the relation between FSWG closure and interior. Now we all know the definition of fuzzy open and closed set. Now here we define FSWG open function. A function h x2y is called FSWG open function if image of fuzzy open set is FSWG open. So we can conclude that every fuzzy open function is FSWG open, but not conversely follows from this example. This is the characterization of this function. A bijective function h x to y is FSWG open if and only if h of interior A less than equal to FSWG interior HA for all fuzzy set A. And for each fuzzy point x alpha in X and each fuzzy open set U containing x alpha, there exists an FSWG open set Y, V in Y containing hx alpha such that V less than equal to HU. This is just one-sided result. This is another characterization of this function. Now we define FSWG closed function. A function h x to y is called FSWG closed if image of fuzzy closed set is FSWG closed. So we can conclude that fuzzy closed function is FSWG closed, but not conversely follows from this example. This is the characterization. A bijective function h x to y is FSWG closed if and only if FSWG closure HA less than equal to h of closure for all for the set A. This is just one-sided result. Now, composition of two Fswg closed functions need not be shown follows from this example. Similarly, for open. But if H1 X2Y is fuzzy closed and H2 Y2Z is Fswg closed, then composition H2 compose H1 X2Z is Fswg closed. Now come to the next section. Here we first introduce Fswg regular space, and FTS xt is said to be Fswg regular if for any fuzzy point xt in X and each Fswg closed set F not containing xt, there exist two fuzzy semi-open sets UV, one containing xt, another containing F, and U and V are not Q-coincident. This is the characterization of this space. X is Fswg regular if and only for each fuzzy point xt in X and any Fswg open Q neighborhood U of xt, there exists for the semi-open set V containing xt and semi-closure V less than equal to U. If and only for each fuzzy point xt in X and each Fswg closed set A of X not containing xt, there exists for the semi-open set U containing xt such that semi-closure U not Q-coincident with A. Now we define Fswg normal space, and FTS X tau is called Fswg normal if for each pair of Fswg closed sets AB with A not Q-coincident with B, there exists two for the semi-open sets UV, A less than equal to U, B less than equal to V, and U is not Q-coincident with V. Now we characterize this space. An FTS X tau is Fswg normal space if and only for every Fswg closed set F and every Fswg open set G containing F, there exists a for the semi-open set H contained in between F and G with semi-closure. We all know the definition of fuzzy cover, sub-cover, compactness, almost compactness, nearly compactness, semi-compactness. Now we define Fswg compact set. For this set A is called Fswg compact if every covered script U of A by Fswg open sets has a finite subcover. If we, in particular, we take A equal to 1x, we get the definition of Fswg compact space. Every Fswg closed set in a Fswg compact space is Fswg compact. This is the definitions of regular space, star regular, normal, star normal space. In an FTS X tau is called FSTG space if every Fswg closed set is fuzzy closed. So we have an important remark that Fswg regular, similarly normal, space is independent concept of fuzzy regular, respectively normal space. Follow from the following examples. And in FSTG space, every fuzzy regular, fuzzy normality imply fuzzy Fswg regular corresponding Fswg normal space. These are two examples, counter examples. Now we come to our last section. A function H x2y is called Fswg continuous function is inverse image of fuzzy closed set is Fswg closed. This is the characterization. A function H x2y is a Fswg continuous function if and only for every fuzzy point x alpha in X and every fuzzy open neighborhood V of Hx alpha in Y, there exists Fswg open neighborhood U of X alpha in X such that Hu less than equal to V. If and only if H of Fswg closure A less than equal to closure of H for all for the set A in X and for all for the set B in Y, Fswg closure H inverse V less than equal to H inverse closure B. Composition of two Fswg continuous functions need not be shown follows from this example. We all know the definition of fuzzy continuous function, so we can conclude that fuzzy continuous function is Fswg continuous but not conversely follows from this example. Now, but if H1 X2Y is Fswg continuous and H2 Y2Z is fuzzy continuous, then composition is Fswg continuous. These are some applications of these functions. Now we introduce Fswg irresolute function. A function H x2y is Fswg irresolute if inverse image of Fswg open set is Fswg open. This is the characterization of this function. And last one, we recall the definition. A function H x2y is called fuzzy pre-semi-open if image of fuzzy semi-open set is fuzzy semi-open. These are the first one is there are some applications of Fswg irresolute function. So many applications are there. Now, we conclude that Fswg irresolute function is Fswg continuous but not conversely. And fuzzy continuity and Fswg irresoluteness are independent concepts. Follow from these examples. Now, let if H x to y be Fswg continuous where y is an FSTG space, then H is Fswg irresolute. And it is clear that composition of two Fswg irresolute functions is also shown. when H1, H2y is Fswg irresolute and H2y2z is Fswg continuous, then composition is Fswg continuous. Now, next definition, a function which x2y is called strongly Fswg continuous if inverse image of Fswg closed set is fuzzy closed. This is the characterization. A function which x2y is strongly Fswg continuous if and only for each fuzzy point x alpha in x and each Fswg open neighborhood v of hx alpha in y, there exists a fuzzy open neighborhood u of x alpha in x such that h2 less than equal to v. It is a remark that composition of two strongly Fswg continuous functions is also so. And strongly Fswg continuous function is fuzzy continuous, Fswg continuous, Fswg irresolute, but converses may not be true in general, follow from these examples. Now there are some applications. These are some applications. Last one, a function which x to y is called Fswg strongly continuous function if inverse image of fuzzy semi-closed set is Fswg closed. This is the characterization. A function h x to y is Fswg strongly continuous if and only for each fuzzy point x alpha in x and each for the semi-open set v in y with x alpha, hx alpha belongs to v, there exists an Fswg open neighborhood u of x alpha in x such that h2 less than equal to v. Composition of two Fswg strongly continuous functions need not be shown, follows from this example. And to remark, clearly Fswg strongly continuity implies Fswg continuity but not conversely, and Fswg strongly continuity is independent concept of fuzzy continuity, strongly Fswg continuity, follow from these examples. So if a projective function, this is the application of Fswg strongly continuous function with fuzzy pre-semi-open function.
Please come to the conclusion.
Okay, these are the applications. References.
Thank you. Is there any question from the audience? If there is no, I once again thank Dr. Bhattacharya for this nice work. Thank you very much.
Thank you.
I would like to request all the participants to present your paper. Just talk within 7 and 8 minutes, and for 1-2 minutes, it is for question answer. So our next participant is Dr. Alauddin Dafadar. Alauddin, are you here?
Yes, I am here.
Please present.
Just 1 minute. Is it visible my screen?
Yes, perfectly. Can you make it full screen?
Yeah, I can make it in full screen also. Is it okay?
Perfect. Please go ahead.
Okay. Good evening to all of you. My presentation is on Whisman quasi-invariant convergence of double sequence of sets. Actually, our previous work was Whisman invariant convergence of double sequence of sets, and we generalize our previous paper Whisman invariant convergence to Whisman quasi-invariant convergence. In this paper, our motto is to introduce the concept of Whisman quasi-invariant convergent, Whisman quasi-strongly invariant convergent, Whisman quasi-strongly Q-invariant convergence, and we make a relationship between among these spaces. Now, the concept of sigma convergent was first introduced by Raimi in reference 18. There is another notion of convergence called statistical convergence, which is most generalized convergence rather than the ordinary convergence. In this case, first we introduce the sigma invariant convergent, and then we introduce the quasi-invariant convergent. Suppose n be a set of positive numbers, we take a mapping from n to n, which is injective by sigma im, which is not equal to exactly m for all I, and sigma im translates into sigma to the power I minus 1 m. A continuous linear functional xi on the space L infinity of all bounded sequences is said to be an invariant mean or sigma mean if it satisfies the following conditions: xi of x greater than equal to 0 for every sequence xn in L infinity with xn positive or 0, and xi of unit vectors equal to 1 and xi of x equal to xi of x sigma n. First, to introduce the notion of sigma convergence, a sequence xn is said to be sigma convergent to the number L if and only if all its sigma limits coincides with L, that is zeta x equal to L. A bounded sequence xn is said to be invariant convergent if limit over all summation of x sigma k equal to L over 1 by p. A sequence x equal to xn is said to be strongly sigma convergent to the number L if and only if limit of p tends to infinity 1 by p sum of all mod of x sigma k minus L equal to 0. The above definition of sigma convergent was generalized by Savas is as follows: V sigma p equal to collection of all sequences such that limit of 1 by p xik minus L to the power p is equal to 0, which holds for all k that is in uniform in k and 0 less p less infinity. A sequence is said to be statistically convergent to L. This is the simple definition. Lim p tends to infinity 1 by p. Collection of all I less equal to p, norm of xi minus s greater than equal to epsilon equal to 0, where the vertical words includes the cardinality of the set. Now, we define sigma statistical convergence. A sequence xi is said to be invariant or sigma statistically convergent to a real number or a complex number s if for each epsilon positive lim m tends to infinity 1 by m, 0 less equal to I less equal to m, mod of x sigma k minus s greater than equal to 0, uniformly in k. And this is denoted by xk tends to ls sigma. Now, these are the simple definition for convergence on sequence of sets. Let x row be a metric space for any point x in x and for any non-empty subset of x. We define the distance from x to a dx equal to infimum of all collection of the matrices rho xa. Let x be any non-empty set. The function psi from n to power set of x defined by psi n equal to n. Then the collection of n, that is a1 to n, is called the ranges elements of phi, and it is called the sequence of sets. Now we handle actually the Whisman convergence of sequence of sets. Let x row be a metric space, capital A be a non-empty closed subset of x. A sequence of closed set ak is said to be Whisman convergent if limit of dx ak equal to dxa. Now we take an example that we ak equal to for all point xy in R2 such that x square plus y square equal to 2kx. As k tends to infinity, the sequence obviously Whisman convergent to the point 0, that is 1 ox is capital A equal to all those points xy such that x equal to 0. This is the definition of Whisman statistically convergent. Limit n tends to infinity, k less equal to n, dx ak minus dx equal to 0, and it is denoted by ak tends to aws. It is an example of Whisman statistically convergent sequence. Ak equal to for all z belongs to C, so that mod of z minus 1 equal to 1 by k if k is a square term equal to 0 otherwise. This sequence is Whisman statistically convergent to 0, but not actually Whisman convergent sequence. Take another example. This is xi for all xi belongs to R2 such that 0 less equal to x less equal to n, 0 less equal to y less equal to x by n if n is not integer square, and x greater than equal to 0, y equal to 1 if n is an integer square. We take capital A equal to for all xy belongs to R2 such that x greater than equal to 0, y equal to 0. And if we take the limit, then we see that the sequence n is Whisman statistically convergent to the set A, but this is not actually Whisman convergent to A. Now it is the definition of sequence of boundedness. Let x row be a metric space and capital A be non-empty closed subset of A. A sequence of closed sets ak is said to be bounded if soup of all the matrices dx ak is less infinity. Now we define Whisman invariant convergent. Let x row be a metric space and capital A be a non-empty closed subset of x. A sequence of closed sets ak is said to be Whisman invariant convergent to A. Why it is called invariant? Because d of x a sigma km equal to dxa, and that's why Whisman convergent turns into Whisman invariant convergent. Let x row be a metric space, capital A be a non-empty closed subset of x. A sequence of closed sets ak is said to be Whisman strongly invariant convergent if mod of that same limit is equal to 0. It is the definition of Whisman invariant statistically convergent. Limit of 1 by n, 0 less equal to k less equal to n, d of x sigma k minus dxa equal to 0. Now we come to our main point, Whisman quasi-invariant convergent. In our paper, we show in the reference, we investigated actually quasi-statistical convergent on double sequence, and also Nare explored some interesting result on quasi-invariant convergent. With the help of these two paper, our previous paper and the paper of Nare, we use actually Whisman quasi-invariant convergent here. First, we recall some definitions on Whisman quasi-invariant convergent on single sequence. Then we introduce into a double sequence. A sequence AK is said to be Whisman quasi-invariant convergent to A if limit p tends to infinity 1 by p dx a sigma n p minus dx equal to 0, and Whisman quasi strongly invariant if mod this holds, and Whisman quasi strongly q invariant convergent if the power is q. A double sequence of set AKL is said to be Whisman quasi-invariant convergent. This is our main definition. A double sequence of sets AKL is said to be Whisman quasi-invariant convergent to the set A if limit of PQ tends to infinity 1 by PQ dx A sigma MP sigma LNQ minus dx equal to 0. Similarly, we introduce Whisman strongly quasi-invariant and Whisman statistically invariant convergent later. First, we introduce theorem. If a double sequence of sets AKL is Whisman invariant convergent to A, then AKL is Whisman quasi-invariant convergent to A. This is the simple proof. Since the double sequence of sets AKL is Whisman invariant convergent to A, then this relationship.
Don't show the proof,
Uh,
just
okay.
the results. Okay.
Okay. Our in this theorem, we actually show that every Whisman invariant convergence sequence, Whisman invariant convergence sequence is Whisman quasi-invariant convergent. Our next definition is a double sequence of sets AKL is said to be Whisman quasi-invariant statistically convergent to A if for each x in X limit of 1 by PQ, KL is equal to P, L is equal to Q, mod under dx A sigma K MP sigma L N Q minus dx equal to 0. Now we introduce a theorem. If a double sequence of sets AKL is Whisman invariant statistically convergent to A, then AKL is Whisman quasi-invariant statistically convergent to A. Here is the proof. Now our next definition is a double sequence of sets AKL is said to be Whisman quasi strongly invariant convergent to A if limit of 1 by PQ double summation dx A sigma K sigma LNQ minus dx equal to 0. And a sequence of sets AKL is said to be Whisman quasi strongly q invariant convergent if whole to the power q to the previous definition is equal to 0. Now we make a relation between Whisman quasi strongly invariant convergent and Whisman quasi invariant statistically convergent. If a double sequence of sets AKL is Whisman quasi strongly q invariant convergent to A, then the sequence is Whisman quasi invariant statistically convergent to A, and the converse is also true. If a double sequence of sets AKL is Whisman quasi invariant statistically convergent to A, then AKL is Whisman quasi strongly q invariant convergent to A. And if we take these two results 1 and 2, then WS sigma intersection L infinity. What is WS sigma? The set of all Whisman quasi invariant statistically convergent to L. Intersection our space L infinity is equal to WQV, Whisman quasi strongly Q invariant convergent, and these two spaces are equal. Now we make a lemma. If for each x in X and for every epsilon greater than 0, there exist numbers P0, Q0, M0, N0 such that for all P greater than equal to P0 and Q greater than equal to Q0 with Mn greater than equal to M0, N0, if the relations hold dx A sigma kmp sigma lnq minus dx ls epsilon, then the sequence, double sequence of sets is Whisman quasi strongly invariant convergent to A. Our next lemma is for any x in X and for every epsilon delta greater than 0 with P0, Q0, M0, N0 taken in the previous lemma for all P greater than equal to P0 and Q greater than equal to Q0, Mn greater than equal to M0, N0. If the relations holds, then the sequence AKL is Whisman quasi strongly invariant convergent to A. And this is our last lemma, and this is the references. We mainly take the references of 2.
Thank you. Thank you. Is there any question? Just have you got any examples?
Yes. Example means which examples are you want?
In support of your results?
In support of your result, no, I cannot search about examples. I am actually generalized this concept from Whisman invariant convergence to
Okay,
Whisman
okay,
first invariant
okay.
convergence.
Nice presentation. Thank you. Our next, Swati Sharma will present. Are
Yes,
you
sir. Yes,
here?
sir.
Please
Yes, sir.
present
Yes,
your
sir.
paper.
Yes, sir. 1 minute. Sir, control my screen. Good evening, all of you. Myself, Swati Sharma, a research scholar under the supervision of Professor Aryan Singh, Department of Mathematical Science, APSU University, Riva.
Can you hold your phone in landscape mode?
Yes, yes.
Yes, it is nice. Please go ahead.
Yes, sir. Today I am going to present my unpublished research paper on title on generalized and projective curvature tensor of para Kanmotsu manifold admitting Jamaica connection. And contents are here. Introduction. The concept of almost paracontact structure on differentiable manifold phi chi eta is defined by I. Sato and state the several properties of the manifold in 28. T. Adati and K. Kanmutsu introduced the notion of parasasakian and sp Sasakian manifold, which on considered as a specific condition of an almost contact Riemannian manifold. The notion of para-Kanmutsu manifold was introduced by B.B. Sinha and K.L. Sai Prasad in 2008. Yes, Jamaico defined the notion of Jamaico connection, which is also known as canonical paracontact connection, whose the erection of paracontact manifold to be parasasakian manifold for a n-dimensional almost contact metric manifold M consisting 1 tensor field phi, one form eta, a vector field xi, and a Riemannian metric G introduced with an almost contact metric structure phi xi eta G. Jamaica connection is defined by equation first. The notion of generalized and projective curvature tensor of type 03 is defined of equation 2, where M denote the M projective curvature tensor and psi is scalar function. The notion of M projective curvature tensor of type 03 is defined by Pokharial and Misra 25 edge and given equation 3, where R denote the Riemannian curvature tensor of type 03, S denoted the Ricci tensor of type 02, and Q denotes the Ricci operator with respect to Levi-Civita connection. In a para-Kanmotsu manifold M of dimension n is greater or equal than 3, the generalized M projective curvature tensor M bar star with respect to Jamaica connection del var is given by in equation 4, where R bar denote the Riemannian curvature tensor, S bar denote the Ricci tensor, and Q bar denote the Ricci operator with respect to Jamaica connection del var respectively. Some properties of para-Kanmotsu manifold admitting Jamaica connection. Theorem first, a para-Kanmotsu manifold Mn with respect to Jamaica connection satisfy Vinci first identity. Theorem second, the curvature tensor of type 04 of a Jamaica connection in a para-Kanmotsu manifold is symmetric first two slots, symmetric in last two slots, symmetric in pair of slots. And theorem 3, if a para-Kanmotsu manifold Mn is Ricci flat with respect to Jamaica connection with, then the manifold is an Einstein manifold. Quasi-generalized and projectively flat para-Kanmotsu manifold Mn with respect to Jamaica connection. A para-Kanematsu manifold Mn is said to be quasi-generalized and projectively flat with respect to Jamiaco connection at if equation 5, where M bar star is generalized and projective curvature tensor with respect to Jamiaco connection delta. Theorem 4. A quasi-generalized and projectively flat para-Kanematsu manifold Mn with respect to Jamiaco connection, then the manifold is an Einstein manifold. Generalized and projectively flat para-Kanematsu manifold with respect to Jamiaco connection del var. In this section, we considered M bar star UVX equal to 0, where M bar star is generalized and projective curvature tensor with respect to Jamiaco connection del var and showing some results. An n-dimensional para-Kanematsu manifold Mn is said to be generalized and projectively flat if the generalized and projective curvature vanishes identically. Theorem 5. A generalized and projectively flat para-Kanematsu manifold Mn n is greater or equal than 2, admitting Jamiaco connection del var is an Einstein manifold. Theorem 6. A delta Xi generalized and projectively flat para-Kanematsu manifold Mn n is greater or equal than 2, admitting Jamiaco connection del var is an Einstein manifold. 7. If a para-Kanematsu manifold Mn admitting Jamiaco connection del var is Xi generalized and projectively flat, then its scalar curvature is constant. Theorem 8. An n-dimensional para-Kanematsu manifold is Xi generalized and projectively flat with respect to Jamiaco connection, provided that the vector fields are horizontal vector fields. Phi generalized and projectively flat para-Kanematsu manifold with respect to Jamiaco connection. Generalized and projective curvature tensor with respect to Jamiaco connection is said to be phi generalized and projectively flat if m bar star phi x, phi y, phi z, phi u equal to 0. From 9. A phi generalized and projectively flat para-Kanematsu manifold Mn adapting Jamiaco connection del var, then the equation is eta Einstein manifold. Para-Kanematsu manifold admitting Jamiaco connection del var satisfying M bar star Xi u dot r star equal to 0. In this section, we considered that M bar star Xi u dot r star equal to 0 and showed a relation on para-Kanematsu manifold where M bar star generalized and projective curvature tensor and R bar Riemannian curvature tensor with respect to Jamiaco connection del var. Theorem 10. An n-dimensional n is greater than 2 para-Kanematsu manifold and an ethnic Jamiaco connection holds M bar star Xi u dot R bar equal to 0, then given equation is satisfied on Mn. Para-Kanematsu manifold admitting Jamiaco connection del var satisfying M bar star Xi u dot S star equal to 0. In this section, we considered that M bar star Xi u dot S star equal to 0 and showed a relation on para-Kanematsu manifold where M bar star generalized and projective curvature tensor and R bar is Dirichlet tensor with respect to Jamiaco connection del var. An n-dimensional n is greater than 2 para-Kanematsu manifold Mn admitting Jamiaco connection holds M bar star Xi u dot S star equal to 0, then given equation is satisfied on Mn and references are there.
Thank you for your presentation. Is there any question? So let us thank again Swati Sharma for his paper. Next speaker is Mayank Pandey. Are you here,
Yes, sir.
Mr. Pandey?
Yes, sir.
Please present
sir.
your paper.
Sir.
Be specific about your results, okay? We are running short of time.
Sir. Good evening to all of you. Myself, Mayank Pandey, a research scholar of and research scholar under the supervision of Professor R.N. Singh, APS University, Riva. contents are here. Introduction. In 1916, a Japanese mathematician S. Sasaki introduced the notion of Sasakian structure 14. A contact metric manifold is said to be Sasakian if it is normal. Yadati and Kakanmachu define para-Sasakian and special para-Sasakian manifold, which are considered as a special case of an almost para-contact manifold introduced by I. Sato and K. Kanmatsu. The notion of Lorentzian para-Sasakian manifold is introduced by K. Kanmatsu in year 1989, later in 1992. The same notion was defined by Mihai and Roshka in Pokharial and Mishra introduced the notion of M projective curvature tensor M of type 04 on a Riemannian manifold MNG of dimension n greater or equal to 3, defined as follows. Day and Paul proved that the M projective curvature satisfy the symmetries and skew symmetries properties of the Riemannian curvature tensor as well as cyclicons. Geometrical properties of M projective curvature tensor have been studied by various authors such as 11 and 18 and many others. Covariant derivative of the M projective tensor is given as equation second. Divergence of M projective curvature tensor is given by on equation third. Matissa and so introduce a new generalized 0 2 symmetric tensor Z on equation 4, where psi is an arbitrary scalar function named as generalized Z tensor. Generalized M projective curvature tensor in view of equation 4 on equation 1 takes the form equation 5, define equation 6 by using the equation 6 and equation 5 reduced to equation 7. The curvature tensor M star UV XY defined in equation 6 is called generalized M projective curvature tensor of Kanmatsu manifold. If psi is equal to 0, then from equation 7 we obtain generalized M projective curvature tensor is equal to M projective curvature tensor. So theorem first, if the scalar function sign vanishes on Kanmatsu manifold, then the M projective curvature tensor and the generalized M projective curvature tensor coincide. Theorem second, a generalized M projective curvature tensor of Kanmatsu manifold is skew symmetric in the first two slots, skew symmetric in the last two slots, symmetric in pair of slots, and satisfy Bianchi's first identity also. A generalized M projective curvature tensor of Kanmatsu manifold satisfying the following conditions. These are first, second, and also third. Generalized M projective curvature tensor of Kanmatsu manifold satisfying RHIX dot M star is equal to 0. In this section, we defined a generalized M projectively semi-symmetric Kanmatsu manifold and proved that some important result on it. Theorem 4. A generalized M projective semi-symmetric Kanmatsu manifold is an inter-Einstein manifold. Theorem 5. A generalized M projective semi-symmetric Kanmatsu manifold is an inter-constant curvature. Corollary. A generalized M projective semi-symmetric Kanmatsu manifold is an inter-Einstein manifold. Generalized M projectively Ricci semi-symmetric Kanmatsu manifold. In this section, we defined a generalized M projectively Ricci semi-symmetric Kanmatsu manifold and proved that a generalized M projectively Ricci semi-symmetric Kanmatsu manifold is either an Einstein manifold or the scalar function psi is equal to minus time and minus 1. Theorem 7. A generalized M projectively Ricci semi-symmetric Kanmatsu manifold is either an Einstein manifold or psi is equal to minus time and minus 1. Generalized M projectively phi symmetric Kanmatsu manifold. In this section, we defined a generalized M projectively locally phi symmetric Kanmatsu manifold and a generalized M projectively phi symmetric Kanmatsu manifold. Obtain an interesting result on it. A generalized M projectively phi symmetric Kanmatsu manifold is an inter-Einstein manifold. References are here.
Thank you. Thank you for your presentation. Is there any question from the audience? Perhaps no. So we thank again Mr. Mayank Pandey for presenting your paper. So next speaker is Ali Ahmed Abdullah. Are you here, Ali Ahmed? Ali Ahmed, are you here? Yes, please speak loudly. We can't hear you. No, you are not audible. You are not audible at all. If you are using a headphone, please remove that.
Hello, am I audible?
Yes, yes, you are not. You are now audible. Please go ahead.
Okay, 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 sir. Is the screen visible, sir?
Yes, perfectly.
Okay. Good evening, everyone. This is Ali Ahmed Abdullah. I am a research scholar in Department of Mathematics, Aligarh Muslim University, under the supervision of Dr. Mohammad Aslam Siddiq. And this is my already communicated paper in uh, some of the journal. And today I am going to deliver a talk on this. My paper is functional identities with generalized derivations on prime rings. This requires some of the definitions and examples and the motivations for us and some of our main results. A ring is said to be a prime ring if and only if zero ideal is a prime ideal in a ring R. Equivalently, a ring R is a prime ring if and only if for every AB in R, if A or B equals to 0, then A equal to 0 or B equal to 0. Prime ring along with some of its associates like the Ottomi ring of quotients Q and the Martindale ring of quotients QR and the extended centroid C can be studied in the book by Martindale named as Rings with Generalized Identities. Here the set P is called Lie ideal if P is an additive subgroup of R which contains the commutator PR. Throughout the paper, we have studied the effect of generalized derivation on the Lie ideals. An additive map F on R is called a generalized derivation if gxy equals to gxy plus x gy, and it is called inner derivation if gx is given as qx minus xq and denoted by q Lie bracket qx for every x in R. If S is certain additive map on R such that SW equals to AW plus WB for every W in R, and for some fixed elements AB in R, then it is called a generalized inner derivation on the ring R. Such map led to the definition of generalized derivation given as associated with derivation mu given as kxy equals to kxy plus x mu y for every xy in R. It is obvious that every generalized inner derivation is a generalized derivation, and for the situation when mu equals to k, generalized derivation is no different from the ordinary derivation. Now we give the definition of standard polynomial identity. The non-commutative standard polynomial given by this, where signature SGN is the signature of the permutation T of the group of permutation S4. Then S4 is called a polynomial identity. This expression is called a polynomial identity if it vanishes on some subsets G. We will make use of this standard polynomial in our study. Here the Lie product x comma y for xy belonging to the ring R is given as xy minus yx, and the Jordan product is given by xy equals to xy plus yx. The Angel condition is given by this, and the skew Angel condition is given by this equation. In this paper, we have studied some functional identities. For instance, the functionality of this, where K is a generalized derivation on a non-central Lie ideal of a prime ring R, where M and T are the fixed positive integers. Here one can see that a K, if we put K equal to 0, then it always satisfies the given functional identity. But the question is whether there is any some non-trivial or non-zero solution to these functional identities. For this, we have studied the given functional identity. Prestigiacomo in 3 gave the characterization of generalized derivation satisfying special yet special typical identities in this theorem. He has studied this functional identity concerning two non-zero generalized derivation, and he come up with the conclusion that either f equals to lambda x or gx equal to lambda raised power kx k plus 1 of x. Otherwise, R satisfies as 4 or R embeds in M2C, where C is the algebraic closure. Ashraf et al. Also studied these functional identities, but for the functional, but for ideal, and taking lead from these two results, we have given our main results. Suppose P to be a non-central Lie ideal of a primary ring R, and associated with R, Q is the Orthogonality quotient, and C the extended centroid, and K is the generalized derivation, and mu is the associated derivation of R. And if K satisfies this functional identity for every xy belong to the non-central P ideal P, and with 6 positive integer m and t, then we come up with the conclusion that R either embeds in M2 over C, or when t equals to 1, then m equals to 1, and if K is the identity map, otherwise K is a zero map. Some parallel theorem are also studied. For instance, for the functional identity of this type, we have uh, given the conclusion that either R embeds in M2 over C, or when m equals to this m equals to 1, then n equals to 1, and K is the identity map, otherwise K is zero map. Similarly, we have studied this functional identity, wherein we found out that either R embeds in M2 over C, or Kx equals to gamma x, where gamma is a member of extended centroid C, such that gamma raised power m equals to 1 and m equals to n. To prove theorem 3.1, these are our prerequisites, the lemma, wherein we studied this generalized polynomial identity, where R1, R2, eta3, eta4 are arbitrary elements of the ring R. Then we have proved that this W, the element of the matrix ring MKSC, is already in C. Moreover, if t equals to 1, then we have proved that W equals to 1, otherwise, and if otherwise, W equals to 0. This is the proposition required for the proof of theorem 3.1, wherein we studied this functional identity, where R1, R2, eta3, eta4 belongs to the ring R, where and m and t positive integer. Then we have come up with the proof that either kx equals to lambda x. Further, if t equals to 1, then lambda equals to 1, otherwise lambda equals to 0. Similarly, the proposition lemma 3.2 is the prerequisite to the proof of theorem 3.2, proposition 3.2, and similarly for proof of theorem 3.3, we have lemma 3.3 and proposition 3.3. Finally, we give the example in support of our assumption that the non-central Lie ideal P is not superfluous. It is always required. Otherwise, our result will not hold. For instance, this example, wherein we took generalized derivation f as this and g as same as f. Then we have come up with a proof that there is some glitch in the result. There is no our result will not hold if we skip the assumption of non-central Lie ideal P. Here we took the central Lie ideal P, this P. So our result does not hold as per our expectations. So this was all for my presentation. This is the reference required for our study and some of our reference. And thank you. Any question will be?
Is there any question from the audience? So let us thank Mr. Ali Abdullah.
Okay, thank you, sir.
Next speaker is Junaid Nisar.
Yes, sir, I am audible.
Please present
Yes,
yourself.
sir. Okay, sir, thanks. Is my screen visible, sir? Hello, sir?
Not till now, it is not.
Yes. Now is visible my screen, sir?
No. Yes, it is visible now.
No, thanks,
Yes.
sir.
Please continue.
Good afternoon, everyone. First of all, I am thankful to this organization for providing me a wonderful opportunity to present my work entitled An Identity with Generalized Secure Derivations Only Ideals. Myself, Junaid Nisar, working as a research scholar under the guidance of Professor Nadeem Rahman, Department of Mathematics, Aligarh Muslim University. My presentation contains 5 chapters. First, introduction. Second, motivation. Third, results on generalized derivation. Fourth, results on generalized secure derivation. And in my last chapter, there are some open problems. So let's move for first chapter, introduction. There are throughout this presentation, we have some following notations. Or is a primary with center or L denotes the non-centrally ideal. F is generalized secure derivation. Q is right martingale quotient ring, and also we know that in case of prime ring, our extended centroid C is a field. So we have some basic definitions. An additive map D from ring orthor is called a derivation if it satisfies D of xy is equal to D of x into is equal to D of x into y plus x dy holds for all xy belongs to ring or. The most natural example is the usual differentiation of a ring over a field F. But in non-commutative rings, it is quite different. For example, in the ring of 2 cross 2 matrices over Z, the map defined on this way is a derivation on OR. Similarly, for fixed element A belongs to ring OR, we define a map D from ring OR denotes by D of x is equal to commutator XA is satisfies D of xy is equal to x dy plus D of xy into y. This derivation is called an inner derivation induced by a fixed element A belongs to R. But it's obvious that every inner derivation on a ring or is a derivation, but the converse need not be true in general. Now we define Lie ideal. An additive subgroup U of ring or is called a Lie ideal of R whenever for any U belongs to subgroup U and R belongs to ring or, the commutator also belongs to U. Here are some examples on any two-sided ideal of R is an example of Lie ideal of R. Center of R is an example of Lie ideal of R. The commutator RR is also an example of Lie ideal of, and the additive subgroup of R containing this is an example of Lie ideal of R. Now we define generalized inner derivation. An additive map F from ring orthor is called a generalized inner derivation if f of x has the form ax is equal plus xb for fixed ab belongs to R. And easily we can see that we can write f of xy is equal to f of x into y plus x iby, where iby is an inner derivation determined by b in ring OR. Motivated by this observation, Bracer in his paper used the composition of two derivations to the generalized derivation. That is, an additive map f from ring orthor is a generalized derivation if it satisfies f of xy is equal to f of x into y plus x dy for all xy belongs to ring OR. This is an example. Other properties of generalized derivations were given by B. Howla in generalized derivation in rings, communication algebra, and T.K. Lee. And also we know that the generalized derivation with derivation D is equal to 0 covers the concept of left multipliers. And also we know that the sum of two generalized derivation is a generalized derivation. So every map of the form of f of x is equal to cx plus dx is also a generalized derivation. Now we define secure derivation. An additive map D from ring orthor is said to be secure derivation if d of xy is equal to d of x into y plus alpha x dy, where alpha is an associated automorphism of derivation D. Here we can easily see that if alpha is any automorphism and I of r is an identity map, then we can say that alpha minus IR written on xy is equal to alpha minus IR into xy plus alpha of x into alpha minus IR of y. So this example is an example of secure derivation of R. Now we define generalized secure derivation. An additive map from ring orthor is a generalized secure derivation if there exists a secure derivation of R with associated automorphism alpha such that f of xy is equal to f of x into y plus alpha x dy. The map D is called associated secure derivation and the automorphism alpha is called associated automorphism of R. This is an example of generalized secure derivation. Now come to my second chapter, motivation. in 2017, Ashraf et al. Shows that if R is a prime ring and F is a generalized derivation of R, satisfying f of xy plus minus yx belongs to center for all xy for non-zero ideal, then the ring is commutative. Later in 2013, Dar approved the Lie ideal version of previous result. More precisely, we can say that if R is a prime ring of characteristic not 2, L a non-square closed Lie ideal of R, F a generalized derivation satisfying f of u into f of v plus minus u belongs to center of R. For all uv belongs to L, then we can say that L is contained in center of ring R. Motivated by these results, in the present paper, we will consider an identity involving generalized CQ derivation or Lie ideals and find the following. This is our main theorem. Let R be a prime ring of characteristic different from 2. L is a non-central Lie ideal of R. F a generalized CQ derivation satisfying f of xy plus minus f of y f of x plus minus yx belongs to center. Then we can characterize f of x is either of the form of lambda x, with lambda belongs to extended centroid C, or our prime ring, or embedded in M2F, where f is a field. This is main form. Now, come to my third chapter, results on generalized derivations. Here, following important factors that has been used in the proof of my results are these. Fact. And this is our main theorem in case of results on generalized derivation. That's if R is a prime ring with extended centroid C. Here f is a generalized derivation satisfying f of xy plus minus f of y f of x plus minus yx belongs to center. Then again we can say that our generalized derivation f of x f is either of the form of ax with a belongs to centroid C, or our prime ring or embedded in M2F, where M2F is a matrix of order 2 entries from field F. Now here is my fourth chapter, that is results on generalized CQ derivation. Here we are going to investigate our generalized polynomial identity satisfying our identity f of xy plus minus f of y into f of x plus minus yx belongs to center, involving generalized CQ derivation. And in the case of generalized CQ derivation having inner automorphism, we get an identity in equation first. Again, this equation first can be written in this form, written as equation second and equation third. With the help of equation third, we can find a lemma. We can prove our lemma, that is if R is matrix of order 2 entries coming from C and R satisfies equation third, then either A1, A3 belongs to centroid, or our prime ring or embedded in M2C, where C is a finite field of characteristic 3. With the help of this lemma, we prove our main theorem, that's let R be a prime ring of characteristic different from 2, L a non-centrally ideal of R, F is generalized CQ derivation satisfying this identity. Then again we show that our f of x is either form of ax, or our prime ring, or embedded in M2C, where C is a finite field of characteristic 3. Now this is my last chapter. There are some open problems. We can solve this. In our identity, there is an f of xy plus minus f of y f of x plus minus yx belongs to center. Here, if we replace x by x power m and y by y power n, then what we can say about the characterization of f and the structure of our prime ring R. Similarly, in the second, if we choose Jordan product, that is xoy is equal to xy plus yx, then again what we can say about the structure of ring R and the form of f. Similarly, in third and in fourth and in fifth, here are some open problems what we can think about these results. And these are references that has been used in my paper.
Thank you, Mr. Junaid. Is there any questions from the audience?
Hello, Nisar.
Yes.
Is there any concept of Lie filter as a dual concept of Lie ideal?
Lie ideal. No, there is a concept of Lie ideal, but I didn't use any Lie filter in my paper, sir.
Is there any concept?
No. This is a simple sort of Lie ideal. That is definition is my first year.
So, okay. Thank you.
Thank you.
Thank you, Mr. Junaid, for your paper.
Okay, sir. Can I stop sharing, sir?
Yes, please.
Okay, so thanks.
Our next speaker is Argotunu Manna. Are you here?
Yes, sir.
Please present your paper.
Am I
Yes, it is
visible?
visible. Yes, visible and also audible. Please go ahead.
Good evening, everyone. My paper entitled with Common Fixed Point Theorem for Fuzzy Mappings in Complex Valued Geometric Spaces. Introduction. Fixed point theory is most interesting and dynamic area of research. This principle plays an important and key role in investigating the existence and uniqueness of solutions to various problems in mathematics, physics, engineering, medicine, and social sciences, which leads to mathematical models designed by system of nonlinear integral equation, functional equation, and differential equation. Banach contraction principle has been generalized in different directions by changing the underlying space. The concept of fuzzy set was first introduced by Jade, which is kept in our references 10. Later, Ruiz obtained many fixed point results for many fixed point theorems for fuzzy mappings in the metric spaces. Hilbert initiated the idea of fuzzy contraction mapping and proved a fixed point theorem for fuzzy contraction mapping, which is a fuzzy analog of Maslow's fixed point theorem for multivariate mapping. Further work on fuzzy mapping can be seen in the references 8. In this paper, we obtain a fixed point theorem and a common fixed point theorem for fuzzy mapping in complex valued complete geometric space. An example is also given which supports the obtained result. Definition. Assume C is a set of all complex numbers for zeta 1, zeta 2 belongs to C. We define the partial order relation on C as follows. If the property P1, P2, P3, P4 are satisfied, then we called it is a partial relation on C, and the properties also hold. Definition. X be a non-empty set and row X cross X to C be a mapping which satisfy the following conditions. Uh, 0 partially related row ZW for all ZW belongs to X and row ZW equal to 0 if and only Z equal to W, and symmetricity condition, and third is the triangle inequality partially. Then X row is called a complex valued matrix space. X be a non-empty set, row X cross X to C be a mapping, and let S greater than equal to 1 be a real number. We satisfy the following condition, only slightly change the triangle inequality here. Row of ZW partially less or equal to S of row ZZ1 plus row Z1W for all ZZ1W belongs to X. Then X row is called a complex valued B matrix space. And the example here, X equal to 0, 1, consider a B matrix space row X cross X to C defined as follows. Then it is a B matrix space with B equal to 2. A point Z belongs to is the known as interior point of the set Z subset of X. If we find 0 partially less than epsilon belongs to C, such that B of Z epsilon is defined as follows. And limit point, definition of limit point are here given. X should be a complex valued geometric space. Zn be a sequence in X. Then Zn is called a convergence sequence if and only if the conditions are satisfied, and the Cauchy sequence if the second condition is satisfied, and called the complete if the Cauchy sequence in X converges to a point in Z in X. X should be a metric space. We define a Hausdorff metric on CBX induced by rho HAB equal to maximum of supremum of rho XB supremum of rho AY, Y belongs to B, for all AB belongs to CBX, where CBX denotes the closed and bounded subset of X, and rho of XB equal to infimum of rho XB beta belongs to B, for all X belongs to X. And this is the example of the Hausdorff distance. We calculate the Hausdorff distance between green line X and the blue line Y. X would be a complex valued matrix space in a non-C subset A is called a bounded from below if there exists a Z belongs to C such that Z is partially less or equal to A for all A belongs to A. Let X row be a complex valued matrix space in non-empty subset A which is bounded from below is said to have the greatest lower bound property or value property on X row if there exists a lower bound W belongs to C such that Z is partially less or equal to omega, where Z is an arbitrary lower bound of A in X, and we write it by infimum of A. And we here generalize the Hausdorff metric as follows. Be a complex metric space, we denote the family of non-empty closed bounded subset of a complex valued metric space X by CBX. Mu belongs to C, represented by S mu equal to Z, belongs to C, such that V is partially less or equal to Z, and the following definition of SAB. Let X row be a complex valued metric space if C is equal to R, then X row is a metric space. Moreover, for AB belongs to CBX, HAB equal to infimum of AB is the Hausdorff distance induced by rho. A fuzzy set in X is a function whose domain X and values in 0, 1. Fx the collection of all fuzzy sets in X. If A is a fuzzy set and X belongs to X, then the function value Ax is called the grade of membership of X in A. Alpha Leibniz set of a fuzzy set A is denoted by A alpha and defined as follows. X be a non-empty set and Y be a complex valued matrix space. A mapping T is called a fuzzy mapping if T maps from X into Fy. A fuzzy mapping T is a fuzzy subset on X cross Y with membership function T of Xy is a grade membership of X in A. A point X belongs to X is called a fuzzy fixed point of a fuzzy mapping T X to Fx if there exists alpha belongs to 0, 1 semicolon close such that X belongs to Tx alpha. Let A and B the lemmas, the A and B to non-empty closed and bounded subset of a metric space X row. If A belongs to A, then D of AB less or equal to Hausdorff metric H of AB. We generalize the lemma. If A and B to non-empty closed and bounded subset of a complex value metric space X row, if A belongs to A, then D of AB partially less or equal to infimum of SAB. The proof of the following lemma directly as a consequence of the previous lemma. Let A and B to non-empty closed and bounded subset of a matrix space X row and 0 less than alpha belongs to R. Then for A belongs to A, there exists a B belongs to B such that D of AB less or equal to Hausdorff matrix HAB plus alpha. And the next lemma is A and B are two non-empty closed and bounded subset of a complex value matrix space X row 0 partially less than alpha belongs to C. Then for A belongs to A, there exists a B belongs to B such that D of AB partially less or equal to infimum of S AB plus alpha. The main result is the theorem 4.1. Let X row be a complete complex valued geometric space with constant b greater than equal to 1. Let T X to Fx be a fuzzy mapping, and for X belongs to A, there exists a alpha X belongs to 0, 1 semi-open closed interval satisfying the following condition: infimum of S T of X alpha X T of Y alpha Y partially less or equal to A1 into rho X T X alpha plus A2 rho Y T Y alpha plus A3 and the A4 rho Y T X alpha plus A5 into plus omega into something, and the following conditions are whole, then T has a fixed point. And the second main result is X row be a complete complex value geometric space with constant b greater than equal to 1. Let ST be two mappings X to Fx be a fuzzy mappings, and for X belongs to X, there exists alpha S alpha T, and the following conditions satisfied, then S and T have a common fixed point. And this is the example. Let X equal to 0, 1 and rho xy is defined as whenever xy belongs to X, then X row is a complete geometric space. Define a fuzzy mapping T X to Fx by Txt equal to Txt equal to 1 if 0 less than equal to T less than equal to X by 4, half X by 2 X by 3, 1/4 X by 3 to X by 2, and 0 X by 2 to 1. For all X belongs to A, there exists alpha X equal to 1 such that Tx alpha X equal to 0 X by 4. And the conditions of the theorem 4.1 also satisfied, and the 0 is a fixed point, so it justified the theorem 4.1. Application and future scope of research. The obtained result for fuzzy mapping in geometric space, fuzzy mapping in complex valued geometric space under certain contractive conditions are helpful for Hausdorff dimension computing, which are helpful in higher energy physics. In higher energy, these results are also helpful for solving the arising geometric problem due to the involvement of fuzzy sets. Further, we can improve the result in bicomplex fuzzy system, and these are the references. Thank you.
Thank you, Argotunu. Is there any questions? Sanjibda, is there any question?
No, Orgo.
Yes, sir.
Hello. So bring your slides.
Amazing.
Just the theorem section. Okay, okay. What this notation stands for? Hello.
Notation, sir.
What this notation stands for?
Which notation, sir?
Yeah?
Which notation, sir?
This one. X row, like X.
X may set a complete complex colored geometric space.
Is
X
there
we are
any
set.
specific name?
No, sir. X we are any set. I use this notation.
Oh, so define the completeness
Yes, sir.
in a fuzzy metric space. In what sense it is defined?
Complete in a metric space.
Hmm.
X is a complete in a metric space. And metric space. Every Cauchy sequence in X is convergent in X.
Okay. Okay.
So thank you, Argotunu, for your nice paper.
Yes, sir.
Our next speaker is Shapon Samanto.
Yes, I am.
Shapon, are you here?
Yes.
Please present.
Okay. Is it visible?
No.
Okay. Right now? Yes?
Till now it is not.
Not yet.
No. Are you from laptop
Yes.
or desktop?
Yes, sir. Now?
So there is an arrow at the
Is it
bottom
now?
of your.
No.
No, till now it is not. Are you clicking on arrow?
Yes. Exactly.
Go for entire screen, okay? After
Yeah,
clicking on
I
arrow.
will say my. Okay. Entire screen. Share. Okay, I think now it will come.
Yes, it
Wait.
is.
Yes. Okay.
Okay, but you have lost 2 minutes.
Okay, sir. No
Go
problem with that.
quickly.
So,
Okay.
good evening to all. So, my topic is Note on Topological Ternary Similarities. Here, our today's discussion based on Introduction Preliminary Topological Ternary Similarities, H-closed and absolutely H-closed topological ternary similarities, completeness, property in it, and references. Okay. So I am skipping introduction portion, directly coming to the preliminary section. To start with the topological ternary similarities, we need some basic definition of ternary semigroups, which is nothing but non-empty set with associated ternary composition, which is mentioned very first. Thereafter, ternary similarities, ternary semigroup which is commutative, each element is idempotent and satisfy the condition for all xy, xxy equals to xyy, and then it is called ternary similarities. And in ternary group, a ternary semigroup is called ternary group for if for ABC belongs to A, the equations uh, have solution in S. Some author says that those equations have a unique solution, but existence of solution says they have a unique solution. Okay. Now we consider ternary similarities, and there we define a relation less equals to if and only if it satisfies this condition, then it can be shown easily that this relation is partially ordered relation, and then we shall say it is a partially ordered ternary similarities. Now we are coming to topological ternary semigroup. Uh, Semigroup is a ternary semigroup is called topological ternary semigroup if there exists a house of topology for which the ternary multiplication is continuous with respect to the product topologies. Now, keeping this in mind, we are defining topological ternary similarities. So, a topological ternary semigroup, which in addition to this is a ternary similarities in the context of algebra, then it is called topological ternary similarities. Here are some definitions related to it. Let S be a ternary similarities and X in S, then we denote lower set of an element X is defined in this form, and upper set of an element which is also defined in that way. And if A is a non-empty subset of S, we define lower set of the set A, which is nothing but union of all those elements X in A, lower set of elements X, and similarly we define upper set of the set A. The relation which we have defined earlier, it is a closed partially ordered relation, and the closure of a topological ternary similarities once again is topological ternary similarities follows from ternary semigroup theory directly. Now, here are some results related to topological ternary similarities. S be a topological ternary similarities and E is an idempotent element. Obviously, E is in S means it is idempotent. Then, lower set of E is SEE, with E is an identity element of this set, and upper set of an element is expressed in this form, and here also is an idempotent element of this, and both these two sets are closed. Now, if F from S to T is a homomorphism from a ternary similarities into a ternary semigroup, then Fs is also a ternary similarities. And if we consider S as a topological ternary similarities and T is a topological ternary semigroup, this image is once again becomes a topological ternary similarities. Now we are coming to H closed and absolutely H closed topological ternary similarities. We are considering a class of topological ternary semigroups. A topological ternary semigroup S is called H closed in this class if S is closed in each topological ternary semigroup T in S. Now, if we consider the class S as a whole topological ternary semigroups, then we call it is a H closed topological ternary semigroup. In the same way, we can define absolutely topological ternary semigroup. It is nothing but just if we replace this H closed by the image of the function, image of this S under some mapping, then we call it as an absolutely H closed topological ternary semigroup. Now here are some main results. A topological ternary similarity says is H closed if and only if it is H closed in the class of topological ternary similarity says. Same result is true for absolutely H closed topological ternary similarity says. Now, in case of union of topological ternary similarities, union is also absolutely topological ternary similarities or H closed topological ternary similarities if they satisfy some additional condition. Conditions are that S alpha is absolutely H closed topological ternary similarities for each alpha in lambda. There exists an absolutely H closed topological ternary similarities G such that G is a subset of S, and this product is a subset of G for each alpha, beta, gamma. They are not same, and then S is an absolutely H closed topological ternary similarities. Same result is held for H closed topological ternary similarities as well. Now we consider S as an absolutely H closed topological ternary similarities and is an idempotent element of S. Idempotent not necessary, is an semigroup. So we are considering E is an idempotent element with EX equals to XE. That means is a biunilateral element. In that cases, we can show that this is also absolutely H-closed topological ternary semigroup, and as a corollary of this, we can show that S is a absolutely H-closed topological ternary similarities, and E belongs to S implies ESS is absolutely H-closed topological ternary similarities. Now, a linear to order topological ternary similarities is H closed if it satisfies the following condition: whenever x and y are two non-empty subsets of S is complete. S equals to sup x if x equals to uh, lower set of x minus s, imply x belongs to X closure. S equals to infimum of y for y equals to lower set of y minus s, implies S belongs to closure of y. And as a corollary of this, we can say is H closed topological ternary similarity, that is linearly order is also absolutely H closed. Now here we just define some completeness type of definitions. Topological ternary similarities is called K complete if it satisfies this condition. It is called S complete if each it will be S complete if it satisfies this condition. C completeness if it satisfies the third condition. Again, a subset of a co-set means partially ordered set is called lower chain closed if infimum of C in A for each chain C is a subset of a possessing infimum of C in X. Upper chain closed if it satisfies this. If it has both upper and lower chain, then it is called chain closed. And keeping this in mind, along with a poset is called chain complete if each chain has sup and inf. And also we called define here a chain closure. Chain closure of a subset A of a set is defined to be the smallest chain closed subset of A that contains A. So it can be said that it is the intersection of all chain closed subset of X containing A. Also, a partially ordered topological space is called well separated if for any points xy there exists a neighborhood v of s v in s of y such that x doesn't belongs to this, and down open if for every open set s of y the lower set is open in s. So keeping this definition in mind, we have two main results. For a continuous homomorphism f s to t from a complete topological ternary similarities s to a topological ternary semigroup T, the image is closed in T if one of the following is satisfied: S or T is down open topological ternary similarities. Chain closure of V is a subset of closure of upper set of V for any open set V of S. T is well separated topological ternary similarities, and X is a subset of upper set of closure of upper set of X for any topological ternary subsimilarities X of S. And finally, last one, if S to T is a continuous homomorphism from a topological ternary similarities S to a topological ternary semigroup T, then image is closed if the following conditions are satisfied: S is K complete, S is C complete, and T is well separated. S is C complete, and S or T is down open. So these are the references. And thank you.
Thank you, Shapan. Shapan, is there any concept of H open topological ternary similarities?
H open.
You have defined H closed.
H closed. Till in topological semigroup context, there is no such type of concept till I believe. Actually, we have taken from topological semigroup theory, but from my knowledge point of view, it is I have not seen till now.
Okay, okay. Thank you. I think this is a very nice paper. Thank you for presenting.
Okay.
And our last speaker is Abul Kalam Mondol.
Yes.
Please present your paper. Shapan, stop sharing. Stop presenting, Shapan.
Okay, okay.
In blue color, you see? In
Yes.
blue base? Yes.
Yes, yes.
Am I visible?
Yes, please.
Good evening, everybody, and thanks to the chair. Uh, the topics of our presentation is almost. Is there any echo? Hello?
It is echoing.
Yeah,
It is echoing.
It is
it is
echoing.
echoing.
I think it is. Uh,
Are you from two gadgets?
no, only on laptop.
Okay, it is okay. Carry on.
Okay. Almost converts to manifold with J belongs to K-Internationality distribution endowed with quarter-symmetric metric connection. There are some basic definition and almost convex manifold and our dimension is smooth manifold with set of tensor field where J is a one tensor field, eta is a characteristic vector field, G is Riemannian metric and which satisfies some conditions. On the product manifold, an almost complex structure is defined by this equation, and almost contact structure is said to be non-null if the above almost complex structure is integrable. According to the Belair, the condition for an almost contact metric manifold it is equivalent to the Navier tensor is vanishes, and the Navier tensor is defined as by the equation leave bracket phi phi xy equal to phi square xy plus phi x phi y minus phi leave bracket phi xy and minus phi uh, x phi y. Now, almost chemistry manifold, according to Jensen and almost contact manifold satisfying equal to 0 and d phi equal to beta, some product phi is called an almost chemistry manifold, and a normal almost chemistry manifold is said to be a chemistry manifold. That is, an almost chemistry manifold is a generalization of chemistry manifold. In an almost chemistry manifold, tensor field defined as L by R x j and h equal to half of the derivative of phi with respect to j, and this satisfying some basic results. And the distribution function orthogonal to j is defined as kernel of beta, and that is exactly equal to image of phi. In a paper, they learned first to show that the almost shear structure is integrable if and only if it satisfies the equation, which is also equivalent to integral manifold of the distribution of Eulerian. That is, if the integral manifold of the distribution are Eulerian, then we say that the manifold is a shear integral almost convex manifold. Um, in the year 2015, Wang Lu gives a result on almost convex manifold with shear integral structure, that is phi q phi minus q equal to this. And in the same year, one gives another result in commutationality distribution with x dash not equal to 0. The DC operator Q of that manifold is given by Q equal to minus 2ni plus 2nk plus 1 eta dx product j minus 2n is dash. And in the another paper, Dello and Pastro gives some basic results on almost Kenmitsu manifold. In also in an almost Kenmitsu manifold with communality distribution, the result nabla x eta y equal to gxy minus eta x eta y plus y gy dash x. In the 1975, mathematician is Gulab introduced a new connection, is called quarter symmetric connection. If the torsion tensor T is of the form Txy equal to eta y phi x minus eta x phi y, which where eta is in one form and phi is on one tensor form, which is a generalization of semi-symmetric metric connection. And the relation given by Gulab in his paper, the that the Riemannian connection and quarter symmetric connection is given by nabla xy equal to nabla xy, nabla tilde xy equal to nabla xy minus eta x phi 1. Nabla tilde is the quarter symmetric connection. And with respect to that connection, the curvature tensor of a sphere integral almost can be manifold is defined as tilde r tilde xyz equal to nabla tilde x nabla tilde yz minus nabla tilde y nabla tilde xz minus nabla tilde lig bracket xyz. And this is the relation between curvature tensor with respect to quarter symmetric connection and Riemannian metric connection. And with respect to that connection, we have studied an almost convex manifold with xi belongs to K-mu dash nullity distribution with respect to the quarter substitution, and we have the following results. The first one is the relation between the curvature tensor between these two connection, and these are DC tensor, which is from this relation it is clear that it is not symmetric, but scalar curvature, curvature is given by S tilde yz equal to syz, and the scalar curvature is given by r tilde equal to r, which is equal, and the number C is the first Bianchi identity with respect to water symmetric connection and Riemannian connection. And next we study the locally symmetric almost K-mesh manifold with respect to the Blatilda, and these are the definition, and we have the result that uh, if we consider an almost manifold with I belongs to K-mu rationality distribution with respect to quota symmetric connection, then the manifold is an Einstein manifold with respect to quota symmetric connection provided K not equal to -2. We also have studied each symmetric orthogonality manifold with is dash not equal to 0 and xi belongs to K-mu rationality distribution with respect to quarter symmetric connection if the condition is satisfied. And here we shown that there does not exist symmetric almost chemistry manifold with h dash not equal to 0 and xi belongs to K-mu rationality distribution with respect to quarter symmetric condition. And finally, we started locally each symmetric chemistry manifold, and we have shown that with respect to that connection, the manifold is an Einstein manifold with respect to that connection, provided k not equal to -2. These are references. Thank you.
Thank you, Dr. Kalam. Is there any questions from the audience? Is your paper published, Kalam?
Yes.
Okay. Very nice paper. Thank you for presenting here. So with this presentation, we are at the end of this session, and I will request all of you do not leave. There will be invited talk by Professor Ruiz. Please stay with us. It will be started in a few minutes. Okay. Sanjita, is Professor Ruiz with us?
Yes, I am.
Okay.
Yes.
Welcome, sir. We'll start the session within a few minutes. Please wait 4 or 5 minutes. There are some parallel sessions going on, and let them come here.
Okay, thank you.
Welcome, sir. Kaushikda, will you please show the Shaha memorial lectures related written some. Thank you.
Yes, am I audible?
Yeah.
And just inquire, I don't know, because this session is over, 4A, and 4C is just now completed. And about 4B, I don't know. So if
Yes, 4B has completed. 4B has
okay, thank you. So I think now we are ready to start this invited talk number 8. And this particular session is, as we can see, this is Shahan Memorial Lecture. And this is the details of these Shahan Memorial Lecture. We can see that this is in memory of two different persons, Mrs. Keel Shaha as well as Mr. J.C. Shaha. So this is all about the details of this Shahan Memorial Lecture. And this lecture will be delivered by Professor Ruiz. And as you can see here, this particular session will be Professor Luis Manuel Sanchez Ruiz for Polytechnic University of Valencia, Spain. And his title of the talk will be Recent Approaches to Continuous Assessment of Mathematical Competencies. And this session will be chaired by Professor Sanjeev Kumar Datta. He is one of the vice presidents of our Calcutta Mathematical Society. So I request Professor Datta to start this session. Thank you very much.
So thank you, Kaushik. Very good evening to all of you. first of all, I convey my heartiest thanks to the organizer for giving me an opportunity to chair the session. It gives an immense pleasure to introduce in this session Professor Ruiz from the Polytechnic University of Valencia, Spain, who will deliver the prestigious Shahan and Shahan Memorial Lecture. So let us first introduce Professor Ruiz. Manuel Sanchez Ruiz. He is currently attached with the Polytechnic University of Valencia since 1980, and he has been the visiting professor at the University of Florida during 1992 to 1999. He has also taught classes in mobility programs at numerous foreign universities. He has published more than 150 papers in reputed journals and conference proceedings on mathematics and engineering. His research interest includes functional analysis in its theoretical and applied aspects and the training of engineers. He is the director of the Research and Innovation Program area of his university, the vice president of the European Society for the Training of Engineers, and also he was a member of several international conference committees. He has also authored several books like Fundamentals of Complex Variables and Applications, Linear Algebra Fundamentals and Applications. With this brief introduction, may I request Professor Ruiz to start his talk. Sir, please.
Sir, your voice is not coming. I think you were muted.
Yes, thanks a lot. Sorry.
Yes, okay.
You're completely right. Thanks a lot, Professor Data, for this nice and gentle introduction. It is for me really an honor to be part of this conference and to take it in this lecture memorial in honor of Saha and Saha, both of them. And what's a pity is that we cannot be all together there in Calcutta. That is something that, well, this is our tough times, and thanks for your effort of all the organization of carrying out this in these complicated circumstances. Thanks a lot. Well, I'm going to start with my presentation. Let's see if I get this. Okay. I think it is visible now. It should be, no? I think.
Not yet.
Not coming.
Not coming. Okay.
Try presentation mode, sir.
Sorry? Let's see.
Yes. Now it's coming. Yes, yes.
It's coming, no?
Hmm.
You can see the PowerPoint now?
Yeah, please open it. Yes. Now please make it full screen. Yeah, it's okay.
Okay.
Now. Yes.
Okay. Thanks a lot. Well, good that technology works, so we can go on. As I go back here, the title is of my talk is Recent Approaches to Continuous Assessment of Mathematical Competencies. This is very much related to my second job that I have got. Main one, first one is as professor of mathematics at the Technical University of Valencia in Spain. And well, yes, I started there very young, really. And I have been lecturing all my life to electronic and mechanical engineers and just to aerospace engineers from 2005. So for 16 years, I have been talking just to aerospace engineers. So this talk has got to do with of the fact that they have been exposed to teach to electronic engineers and aerospace engineers now at this moment, and that because of it, well, I got close to CEFI. I will say some words about CEFI. And then this has been very enriching, really, for my teaching and for personal experiences. And more than that, I mean, if you overview my students, you can see how I have been moving. The first one was about locally convex spaces. That was my origin. That was functional analysis. And the second one had got to do with a study of medical images to study the neuroblastoma illness with infants. That was in computer science. And the third one was very related to the talk that I am giving now. And the fourth one, it is about the haptic generation. That is the new generation that is coming nowadays, and that will fill our classrooms in very soon. In fact, some of them are starting to arrive now. They are native digitals, and we are just immigrant digitals in this digital world that is coming nowadays. In this talk, I will say, as I have mentioned, some words about CEFI and how this is structured and how it is working on mathematics for engineering education mainly. Now I will say some words about mathematical competencies. That is very hard to define. It's not so easy. We have got some ideas, but really in CEFI they have done a wonderful work trying to structure all these ideas. Then I moved to continuous assessment, and to continuous well, that was the main title of the talk, present approaches to continuous assessment. And finally, I will say some words about something that we have been implementing really with our space engineers for more than 10 years here at Technical University of Valencia to create them. Well, CEFI is the European Society for Engineering Education. It was created almost 50 years ago in Belgium. It is a non-governmental organization, and that means that it is maintained and sustained by its members, and its members are us, universities, and individual members, mainly from Europe, but also there are some people from other parts of the world. And well, we pay our fees, and from that we have got an office and some general secretary there in Belgium, in Brussels, and we gather together in once a year in an annual conference that covers all disciplines. That I will go through that and just very soon. And really, CEFI is doing what its members are concerned and we are worried about. It has got institutions from 40 countries. Not all universities are member. It's more than 100, but not all. There are perhaps 4 or 5 in Spain, something similar in other countries. But anyway, it is an inclusive organization that gathers people that are concerned with engineering education. The aims of the associations are to promote the information to the general public on engineering education, to improve the communications and exchange between teachers, researchers, and students, to develop cooperation between engineering educational institutions. This is done many times because sometimes when there is some call in Europe and that there are possibilities to apply and to get cooperation, well, perhaps we set up some meeting to see what institutions are interested. And this is always interesting. I recall that 5 years ago, yes, it finished a program that was called Ideas, and by means of that, we received, it was possible to receive students from India, Pakistan, Malaysia, and Bhutan. So from that, usually these calls are organized by different parts of the world, and sometimes there are possibilities there to collaborate really. And through that call, we received all types of um, 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 people involved. I mean, we see the students from undergraduate, master, PhD students, professors. So there are sometimes courses so that CEFI is aware of and usually keeps an eye on it. And when it's convenient, we try to develop cooperation between different institutions, because sometimes it is required that at least 2, 3 countries are involved, or 4, depends on each call. So CEFI keeps an eye on that. And we also try to keep cooperation with the industry and education institutions. And we contribute to the development and improvement of engineering education in general in the economic, social, and cultural framework of Europe. In addition to our annual conference, CEFI has got different special interest groups, and that is to try to connect the educators and students, industrial stakeholders, but just with some particular interest inside engineering education. They are very, very wide. It's not just for disciplines. These groups organize meetings, workshops, write position papers, and participate in the European projects. It's important that sometimes the groups gather independently from our annual conference. And for instance, the mathematics working group, that I suppose that may be the more interesting for you, engages in the discussion about the role of mathematics in engineering curriculum, its practical application in professional life, and the use of technology, and the ways of teaching, learning, and motivating students, as well as forms of assessment. Every 2 years, the mathematics working group develops its own conference. That's usually done in April, May, more or less, and that is done every 2 years. The annual conference of CEFI is done annually. So this year has been virtually, online, and we hope that next year, with the vaccine being generalized, we will be able to make the coming events presential face-to-face again. In addition to mathematics group, we have got the physics special interest group, the engineering education research, that is for people that are doing research in engineering education. We have got open and online education, continuing education and lifelong learning, sustainability, gender and diversity, attractiveness. Attractiveness has to deal with to try to attract the best students, to make engineering studies appealing, so that the best students apply for engineering. So that has got to do with develop activities at a secondary school and things like that, so that people, students, can see that in theory engineering is something that not for weird people, is that something that is all around us. So try to make that appealing, so that in everyday life there are many moments where engineering is behind of each of our acts and movements. We have got also a working group working on ethics, curriculum development, engineering skills. So as you can see, it has got to do not only with technical, technological, scientific disciplines. It covers other ideas like ethics, that is to promote ethical behavior inside the engineering education. That is important. That is important for some people. This obviously these special groups sometimes interact, because there are mathematics, gender, physics, curriculum development, online learning may be interesting for some mathematician lecturing to engineers at some given moment. So they are not closed; they are open, and people can approach to these working groups. And in what concerns the mathematics working group, it was created in 1982. So that was 9 years after CEFI. And we obviously think that mathematics is at the heart of engineering. It is in both the language to express ideas and the means to communicate result in a clear technical way, And an effective study program in mathematics for all engineering students is a necessary requirement for the education of qualified engineering graduates capable to continue becoming more specialized, or just to go to the work and professional work, and that where technology is changing, so they need to handle mathematics, so that they are capable really to change technology and to get updated to the new softwares, technologies, and things going on. That nowadays we go very fast compared to the previous generation, and it is very clear that when an engineer graduates, he doesn't know all the engineering skills or maths that he or she might need for professional tasks. I mean, he or she will have to update continuously. So the aims of the mathematics scientific special interest group include, well, to provide a forum where we can exchange our views and ideas that we are interested in the use of mathematics by engineers, to promote a fuller understanding of the role of mathematics in the engineering curriculum. That's very important, because sometimes even with our colleagues that also are lecturing to engineering degrees, sometimes they are not so appreciative about the role and importance of mathematics, to foster cooperation in development of courses and support material in collaboration with industry, and to promote and recognize the importance of engineering education. As a consequence of this working together, the mathematics working group took the challenge of studying in depth the importance and the relevance and what is a mathematical competence, mainly thinking about engineering education, but their principles may apply to other parts and of the other disciplines. And after a long iteration, because this took a long iteration, this wonderful handbook came out. That happened in 2013. It has been very recently updated. They have gone back 2 years ago. They have updated it slightly, and this is very easy to be to have access to it. I mean, just writing a CEFI mathematics working group or something like that, as or a special interest mathematics working group. At the end, there is a link with Allen University in Germany, where this guidebook is located. And well, if anyone is interested and doesn't get to it, I will provide the direct link, because really it is very easy. Yeah, it was done when at that moment Burkhard Alpers was the chair of the working group. Each working group has got a working group that usually lasts for 2 years, and at that moment, these were the editors that helped her, and in fact, Daniela Belikova succeeded to Burkhard Alpers as chair of the working group after he finished his term. And in this booklet, you can find a long discussion about mathematical competences, and they worked very hard. And there was, well, usually, as it happens in science, we never start usually from scratch. There are always some people that have been working on the same issues in advance, and well, we can take advantage of that, and that is what they did. There was a project that was a Danish project that had been working on these ideas. and they got 8 competences, and putting all together, it was general overall competence that was important for engineer. So what the SEFI framework did, it was to modify it is slightly, and they presented the 8 mathematical competencies that they are very exhaustive, and really this gives, as I have told you, really to possibility to future research, because it's an ongoing project, and there are many features that still can be developed. So there are 8 mathematical competencies that are pointed out. Some of them are very basic. For instance, they are thinking mathematically, and this competency comprises a knowledge of the kind of questions that are dealt with in mathematics, and the types of answers mathematics can and cannot provide, and the ability to pose such questions. It includes the recognition of mathematical concepts and an understanding of their scope and limitations, as well as extending the scope of by abstraction and generation of results. This also includes an understanding of the certainty of this that mathematical considerations can provide. So that is the competence of thinking mathematically. Reasoning mathematically, this competence includes, on the one hand, the ability to understand and assess an already existing mathematical argumentation, that is a chain of logical arguments, in particular to understand the notion of proof that something is complicated. Well, I suppose that you all are suffering with that from time to time, and to recognize the central ideas in the proofs. It also includes the knowledge and the ability to distinguish between different kinds of mathematical statements, difference, if-then statement, if and only if statement, and so on. On the other hand, it includes the construction of chains of logical arguments, and hence of transforming heuristic reasoning into own proofs, reasoning. Third one is posing and solving mathematical problems. This competency comprises, on the one hand, the ability to identify and specify mathematical problems, be they pure or applied, open-ended or closed, and on the other hand, the ability to solve mathematical problems, including knowledge of the adequate algorithms. What really constitutes a problem is not well defined, and it depends on personal capabilities whether or not a question is considered as a problem. This has to be borne in mind, even, for example, when identifying problems for a certain groups of students. Modeling mathematically, that is something that we all deal with quite a lot with when posing some applied problem. And this competency also has essentially 2 components: the ability to analyze and work in existing models, find properties, investigate range invalidity related to model reality, set up a mathematical model and transform the questions of interest into mathematical questions, answer the questions mathematically, interpret the results in reality, and investigate the validity of the model, monitor and control the whole modeling process. And this competition has been investigated in the past also by Blumhoff and Jensen. As I told you, there is an advantage to rely on Atlas shoulders that have been working previously. The fifth one is representing mathematical entities, and this competency includes the ability to understand and use mathematical representations, be they symbolic, numeric, graphical and visual, verbal, material objects, and so on, and to know the relations, advantages, and limitations. It also includes the ability to choose and switch between representations based on this knowledge. So that is representing mathematical entities. Sixth is handling mathematical symbols and formalism. This competency includes the ability to understand symbolic and formal mathematical language and its relation to natural language, as well as the translation between both. It also includes the rules of formal mathematical systems and the ability to use and manipulate symbolic statements and expressions according to the rules. The last 2 ones are communicating in, with, and about mathematics. This is very important. This competency includes, on the one hand, the ability to understand mathematical statements, they may be oral, written, or other, made by others, and on the other hand, the ability to express oneself mathematically in different ways. The eighth is making use of aids and tools. This competency includes knowledge about the aids and tools that are available, as well as their potential and limitations. Additionally, it includes the ability to use them thoughtfully and efficiently. This has got to do with the use of mathematical software and technology and modern technologies. These competencies frequently overlap. Sometimes the aspects of one competency is also needed to develop another one. But when they speak about each competency, they try to emphasize peculiar aspects, and for that reason, they are separated. In general, we can group them. The first one cluster will be the first four ones. It is the ability to ask and answer questions in and with mathematics. And the second cluster, it will be the last four ones, maybe the ability to deal with mathematical language and tools. Well, this has got to do with mathematical competences. But when you are speaking about mathematical competencies, and the mathematical competency may be putting together of all the previous dissection of what a mathematical competence is, then there are also other aspects that you might consider, and they are the degree of coverage, the radius of action, and technical level of each competence. The degree of coverage is the extent to which the person masters the characteristic aspects of a competency. That is, how many of these aspects, how many of these aspects the person can activate in the different situations available, and to what extent independent activation takes place. So that it means that you have got a competency, but sometimes you are not skillful enough in order to realize that you can apply that in a different context. And the second one is very related to that. That is radius of action. That is the spectrum of context and situations in which the person can activate that competency. For example, if a person can solve problems dealing with arithmetic, algebra, geometry, and probability theory, he or she has greater radius of action than a person who can only manage arithmetic and algebra. If you go to more tools, you can apply that in more different situations. And finally, it is the technical level of a person's competency is determined by how conceptually and technically advanced the entities and tools are that can be activated in the relevant competency. For example, a person who can sketch graphs for real functions of one variable, but not for two variables, has a representing competency at a lower technical level than the person who can do both. So you got an idea about calculus, but you have not got in the with depth enough, so that when you are challenged with problems that require several variables, perhaps you cannot yet, but you are starting. That is very common when you put a subject analysis 1, 2, 3. Obviously, you are improving your analytical competencies as along you are advancing. So how to reach these competencies? Well, through activities. We learn through activities. When we language through activities, listen, speak, and that takes a lot of time when you are very young. And when we want to go fast with mathematical competencies, the basic idea is that you need to execute a lot of activities, and that is what sometimes in advanced modern technologies you use a lot of tools. Usually you do more than lectures and written exams. That is the traditional things. But I suppose that some of you will also use math labs like Derive, Mathematica, or MATLAB, or some of these software. You can place also assignment, put some quizzes, 1 minute. We can do some homework assignments. So there are many possibilities. The idea is that you need to do activities to reach mathematical competencies. How to evaluate them? Well, it seems that you must do some follow of what is going on to see how the students are progressing. And for that, continuous assessment seems to be adequate. Assessment usually is intended to measure what a student has learned and the competences that they have developed. The continuous assessments try to do this more often. So in general terms, a greater granularity, that means the more activities that you are controlling and you are looking at, should provide a vision of the student's performance within the learning process. So in order to get mathematical competences, we should try to develop a procedure to obtain a continuous assessment environment. That is very important. If you are the only one that is doing these things in a university institution, then things are very complicated. If it is the whole institution, things are much easier, because then it is what most people are doing. But for this, you also need to, well, to get some consensus, because if you abuse of these continuous assessment, then the students may have the sensation that they are just doing work, and there is some risk that you get only shallow learning. So that means that sometimes when you're doing this continuous assessment, you mustn't lose that of sight that this is everything is a formative assessment. So this is a training cycle. It's important that the students perform, that you are controlling, and that they are progressing, and that they are showing how they are achieving their mathematical competences. And then not all of them have got the same value, obviously. Always there must be some relevant, they are discrete moments of evaluation, some moments that are important, and that you can do a lot of these things, but at some given moment, obviously, and usually we do, you must do some relevant moment of evaluation to test how the students have been progressing. Well, we checked, but because to check everything is impossible, so the objective have always to be feasible. We check that just the mathematical guides, because we, according to regulations, always have got to be accessible and visible. So really, through internet, you can check at any Spanish university what are the competences, and not just the syllabuses of each subject, and looked how many provided information about competences or mathematical competences or continuous assessment. And here you have got the document that we analyzed just with mathematics subjects in aerospace. Aerospace is not given in every Spanish university. So we looked at some total 35 different documents of different mathematics subjects, and you can see in blue how many just mentioned with more or less depth. So you see that really they are mentioned, but sometimes in some of these, like a relation between competencies and activities they are doing, or other exams different from written exams or lab practices. So they are coming more general in Spain, but we still have got to advance also. So in order to develop these ideas, what we had in mind, and that usually we are lecturing topics of calculus, line integrals, surface integrals, and whatever. So usually these topics are partially ordered. So there is a progression. And so the set of activities should be introduced, obviously, for the students' training. And the activity that they should be doing, they should cover a desired grade of improvement of the 3 dimensions. So that means that you must provide them more tools and with more depth. And obviously, when you are getting some competency, that competency is going to be used later on. That is something that we thought it was relevant. And for that reason, we thought that the moments of evaluation should not be considered independently. each time that you are doing, and this has got to do mostly with the relevant moments of evaluation, they are based on the previous moments of evaluation or the previous actions they have been doing. So when a student performs well in previous activities, it is more likely that he or she will do it better later. So we should take advantage of this of these activities, all these previous moments of assessment. And if here things go better than here, it means that all these activities have had a positive impact, and that the student has improved. So really, if you are giving some weight or some value to these small activities that perhaps sometimes you give some value, well, then perhaps you should change the value that you gave, because, well, perhaps he got here just a 4, here a 6, and then he gets here a 10. Well, that means that these activities were well really structured, and he has been improving. And really, even though little, it's not clear that if you had taken only a final exam, the final grade will be this one and will be better than this one. So we thought that we should have this into consideration. This is very complicated, and depends on the studies, if it's semester, annual, subject, the structure, the institutions, and but this was something, the thing that we had got behind. So we started to develop this idea, to try to think about. And this is brought out what we call dynamic assessment or dynamical assessment. It meant that somehow that, well, sometimes you have got to decide when this improvement or this really these activities have had an impact in ulterior exams, how to consider it positive or negative contribution to the previous one. Because, well, if a student has done here very well, and then it comes to the relevant moment of evaluation and he does it very poorly, it means that something is failing, or these activities were not well posed, or these were not well evaluated, or he got an extra help that perhaps you were not able to detect, and then here things are failing. So perhaps, even though little, you should put here some negative weight. But we don't do that. We really, when we post activities, usually when it is formative, the weight is very little, very small, really very small. So really, the effect is always positive. So that if they perform well, then we are well. There are many possibilities. You can replace the full grade here. We don't do that. Because we also, when we say we, I mean here at the UPB in Valencia, Spain, we try to encourage people to do the right things at the right time and not to leave it for the last day. So we sometimes, when the student has got all competencies in all the different parts of the subject and not only in one, and has improved, then perhaps we replace this previous grading perhaps in 50-50 or something like that. So that really they got an improvement here, having in mind what they have done better later. But if they perform negative or worse, we don't change this, because we want always students to face everything in a positive way and not to have fear of bad consequences. We try to be positive. So really, that is very, very important. But that, as I mentioned, that is something that has got to be thought according to the situation, each university, each condition, each regulation. Sometimes you can do this, in other places you cannot do that. I am aware of that. Here it explains, for instance, how we started to develop these ideas with our special engineering students. We have got activities of assignments, workload, also lab sessions, weekly sessions. This is an annual subject run from September to June. They have got here a lab exam at the end of the first, more or less after Christmas, at the beginning of January. This is at the end of May. So, and they have got different partial exams of theory, problem solving mainly, but they are supported by other activities. Have got first, second, third, fourth. There is a clear relationship between 1, 3, 4. 1 is one variable calculus, 3 is several variable calculus, 4 is series, and TP2 is algebra. Well, that has got an influence on everything, but is more independent somehow. But here in TP4, what we do is that really in TP4, this is not a final exam, but in TP4, we always include several questions that have got very little weight inside TP4, but really the content has got to do with TP1 and TP3. So really, this becomes an exam where we are concentrating on the last part of the subject, but we include previous part of the subject. They have got very little value, but so if they don't do it, well, they are missing the best mark. But however, for us, that is very useful because that works as a relevant moment of control to check if the previous competencies that were taken a long time ago, well, they have got to go back again to review, to look at the small details, and so that provides an occasion to check if they can really achieve those competencies or they improve them. That is very common and logical, because you have been working on these topics while working on TP3 and here on a special purpose to go back. So really you can have improved your competencies. And that is something that we try to encourage. So the students have got the idea that when you get a 6, that is a good mark, 6 you have passed, well, you can improve that. Keep working. So we will pay an eye on it, and you can show it to us. So perhaps you can improve your mark without doing anything, just by taking your standard exams. We look at it. Well, and everything of that at the end comes a final grade, and that's what we call DCDA. That is a dynamic continuous discrete assessment. As I mentioned, we have been using this for more than 10 years, and the blue part is the students that passed the subject, and red is the ones that fail, and the green is the ones that drop out. With this system, it's very complicated to have dropout students. Well, if they drop out, it's because they want to drop out, because we insist them quite a lot, even though they get a bad mark in the first exam, that is not relevant. At the end, they also can try to retake the exam, but even not reaching that situation, they can pass the subject. If before that, they show that they have got those competencies in other exams. And for that reason, dropping out is something that it is very complicated. But obviously, if for any reason the students want to drop out, that is something that you cannot avoid. But usually, our numbers are very, very low in dropping out. When you ask about the last exam to the students about what is their opinion of that, because and for this is very important, is that we only use this last exam in a positive impact on previous grades. So most of the students are very positive about that. Very few think, well, some of them do not like to retake exams that they have passed. Why? What for? If I already passed, why are you asking me that again? Well, that is something that you cannot avoid. And we also distinguish. It was anonymous, but we distinguish between the grading that they had got previously, and in general terms, better students that have got a higher degree, well, have got a positive perspective that by doing this, their competencies are improving. So that is with the bad students, that is more complicated to get that, because, well, they are answering to another thing. Some students are very biased, and they answer sometimes according to how the things are going on. No, they do not analyze the system itself. So, and I am going to finish. The main conclusions that I would like to point out from this dynamical continuous discrete assessment that we have been performing for more than 10 years, and that they are inspired by the CEFI position paper. We worked quite a lot on that about mathematical competencies and grading and continuous assessment. It is that it has been encouraging the improvement of previously assessed competencies in the change of topics. So if you pass something, you can improve that grading. So that don't be happy with just your grade. But that doesn't mean to take again that exam. No, you don't take that exam. We never do exams just for improving your grade. No, we assess your performance continually with what you are doing at the expected relevant moments of evaluation. That is something that we don't do. We don't do just a specific exam to improve. We evaluate that as a continuous assessment according to the performance. Well, it has facilitated that all expected levels of competencies are achieved because we are continuously reviewing what they have been doing in the past. It has received a favorable perception by students that have been evaluated with this dynamic and continuous discrete assessment. It is really flexible. It is not closed. There are many ways that you can play here, different ways of retroactivity. You can play some conditions. Well, I will take this improvement just when they have got all minimum desirable competence in every part of the subject. That may mean in lab sessions, in algebra, in calculus, so you only improve grading to the students that really have got the minimum in each part and has improved in some part. And avoid the situation that if a student has not got what you consider a minimum competency in one part, let's say algebra, well, then you don't improve the ones that might change what in beginning was the fixed grading. There are always some percentages that are fixed, and if they don't, I mean, that is fixed. What you can do is get more than what you expected because you are performing better in previous evaluated competencies, because later you show that you know how to handle them well. That is the key idea. And from that, it is flexible. So you always have got to fix the rules, obviously. That is 10, 23, 37% or whatever, that is fixed. And at the end, your final grade is that one or better. Better how? If at the end, this is a long run. It's important that at the end you are well trained. It's not important that you start very well and then you start doing worse at the end. Well, then your grade is what it is. Period. You have not improved. So this is a system that really encourages people to keep working, and facilitates the awareness of shallow learning hazards, because there are some relevant moments that they are deep and not just activity for 1 week or of the last exercises. Well, the main ideas of this process, well, we published them in the mathematics journal just very recently, really just after the summer, or in the summer it was finished, so that has been approved, and we are very happy about that. And well, just finish with this. Well, it happens that there are many sentences of Albert Einstein that we don't know if they are true or not, and this has got to do with assessment and continuous assessment. Not everything that can be counted, you can count many things, counts. Not everything. You can count many things, perhaps they should not count, and not everything that counts can be counted. Not everything that is important sometimes can be measured, so that is very complicated. We try to evaluate the mathematical competencies of each student as a whole, not just by finding averages of grading. So we sometimes, obviously, we go over and go on and what has happened, why that student failed or didn't get the maximum, and check what if that was important, not relevant, and this takes time, obviously. That is a problem always for instructors, and the time. But with students that are there in the middle, that is not clear, then we go a thorough study on them to see what are their real mathematical competencies, and not just the grading they have got in all the exercises. We have got at the end huge access with a lot of grades, because we are doing lab sessions every week. They are we do assignments, we do relevant exams with computer that they are done individually and under environment, controlled environment. Obviously, in traditional problem solving of exercises, so we get a lot of information. So we pay close attention to these students, and also to the best ones, because usually the maximum honors qualification, we give the maximum. We have got the maximum that we can give by according to the Spanish laws, and then we study in those cases with more detail. Well, and that's it. Thanks a lot. It has been really an honor to participate in this Shahan Memorial Lecture. So now the chair comes back, and if somebody wants to ask something, I'll be happy to answer if I can. Thanks.
So thank you, Professor Ruiz, for your nice and dynamic deliberation, and really we enjoyed the lecture. Now, any query or comment from the audience? So if not, so I have a question, Professor Ruiz.
Yes, tell me.
So under the flavor of your lecture, what is the message for minimizing math phobia amongst the school students?
Well, that is very complicated. Usually, it has got to do with the personal character of the instructor. that is one very important thing, to try to empathize, to get close to the students, and to try to place as many as possible examples that are applied, that is a mechanical application, that is an aerospace application, that they can see in aeroplanes, rockets, or some examples where they are using their math. There are training experiences that are useful. For instance, try to get some of your third or fourth engineering students, and that they are willing to and come and help, or someday optionally and voluntarily invited by you, can give some example or some class where they have used double, triple, or some kind of the math they are learning. So that might help, just to provide an insight that they can see that the things that they are learning, perhaps sometimes it is tough, well, because learning is tough. It's like if you want to be an athlete and you want to run a marathon, well, perfect, but behind that there is a love. Tough training sometimes is not so nice, and then you suffer a lot to see you the advantage of this, but having the help of students that have passed, that can show that their maths are useful to use. Well, and that is important to talk with your mechanical, electrical, electronic colleagues, so that they can see that where they are using mathematics and use their examples, and so they can see, well, this is a problem that you're going to use in second year, third year. Let's do it, and then they can use that is useful, and obviously to include software, mathematical software, to use Mathematica or some visualization, so that they can see that when there is a big companies that have spent so much money in developing this software, and that really they avoid the tedious of doing tedious calculations, but you need to know what to ask to the software. Well, all this helps, but it is very complicated. So that means that, and the things are becoming more complicated with the new generations. There are many examples of gamification. Try to do some kind of games or something like that, so that they are playing while they are learning. What is important is that activities have got to be planned in advance but to try to just and that for engineering students is important, not only the theorem proof and mathematical problem, because then they think that is not useful for them. So we need to make an effort to approach to their point of view. So we need to do it, and obviously we have got much more base, and we know that things are important. And obviously you can play some counter example or something that it looks something that logical, and you do the math, you see this doesn't work. Perhaps there is something that is failing here. There is some hypothesis that you have missed also. So the answer is that there are many things to be done, but it's many, not only one. There is not an easy recipe.
Yeah. So any other query or comment from anybody? So if no, let us give a big hand to Professor Ruiz. Thank you, Professor Ruiz, for your nice lecture. Thank you.
I think my pleasure. Thanks a lot.
Yeah.
So thank you very much, Professor Datta, for wonderfully conducting this session. And thanks to Professor Ruiz for his very informative talk, I should say. And now we are at the very fag end of this 3 days program. We are now going to conduct the valedictory session. And I think Dr. Rajat Banerjee is one of the very senior council members of Calcutta Mathematical Society. I think he's there. And I will request him to, we are just within the time. So I request Professor Rajat Banerjee to start this valedictory session.
I think I'm audible to you, to all of you.
Yes.
So good evening, everybody. Finally, the curtain comes down for the International Conference on recent development in mathematics and mathematical sciences. Every year, we organize this type of conference in person during the month of December. But as you are aware, due to this pandemic situation, last 2 years, we are arranging this conference in the virtual mode. For the present year, the selected themes are analysis and PDE, commutative algebra, finite element method, Lie group and abstract, harmonic analysis, machine learning and data science, mathematical epidemiology, operator theory, system biology, topological graph theory, entropy estimation application. It is our pleasure to state that eight very eminent person has delivered their invited talk in their respective field. We appreciate them for giving this lecture in spite of their busy schedule. So finally, this lecture, basically, it has become the yardstick for the future researchers who want to work in different areas in future. We got around 150 participants from different corners of the globe. We have finally selected about 114 abstract for contributed oral presentation. We are glad to inform you that except one or two, all the presenters presented their works. This huge number of oral presentations went parallelly. We are planning to publish some of the manuscript after peer review process in our esteemed journal, Vice Journal of Calcutta Mathematical Society or Bulletin of Calcutta Mathematical Society. We will inform the procedure later. Most of the contributory papers dealt with new concept, which is quite appreciable. We are delighted that CMS has been instrumental in bringing the world in one place, where researchers from around the world, including India, got a platform to present their work. So in one word, pandemic do cause great harm to the mankind, but it also opened up a new digital platform where researchers who are unable to attend physical conference can now present their good work in virtual mode. Now, with this word, I will ask Dr. Alok. I think Dr. Alok will there will be some presentation. I think Kaushik, Dr. Kaushik.
Yes, this will be actually some mathematical ability tests was already performed, and we have selected 4 different students out of all these candidates, and they are actually the highest performers. And I think Dr. Bablu Vishesh is already ready with all this
Fine.
different information.
So, Dr. Pavlovicius, please can you start saying the names of this recipient?
Sure, sir. In this test, this year we arranged the mathematical ability test for 11 and 12, and it was decided that 4 participants will be awarded, and from different parts of India they participated, and among them we have here 4 participants. The name of the first participant is Aditya Kishore, Loyola School, Trivandrum, Kerala. If Aditya is here, I would like to have you in video mode.
Yes, sir.
Aditya, are you here?
Yes,
okay. Sir. This is Aditya. Congratulations to you. He secured the first position in this advanced mathematical ability test. If you like to share your thought or feelings, you can share with us.
Thanks a lot. It was a great test, and it was a wonderful experience too, especially the interview part. And then all the professors who asked me questions are also very good, and it was very challenging also. Thanks.
Thank you very much. Big clap to Aditya. I will show your certificate of excellence here. So I have to share my screen first. So give me 1 second. So this is your certificate, Aditya, for your achievement. And for the audience, I will mention that 3,000 cash award will be given to Aditya Kishore after this session, and I think within 1 or 2 days. So congratulations. This certificate will also be given to you through your email. So thank you, Aditya.
Thank you, sir.
Our next participant is next award is owned by Shiona Jena from Pratt Memorial School, Kolkata, and he secured second position. I'd like to see Shiona. Are you here?
Yes, sir.
So
Yes,
open
sir.
your video mode. Just let me.
Yes.
I think we'll be out of this presentation. Yes. Congratulations, Shiona. Big clap for
Thank you.
her.
She secured the second position in this conference. If you like to share a few words with us, please.
So it was a very interactive experience and I really enjoyed the interview part, and I could also learn many things from the interview, and I could research about new things from the interviews, about the questions which I could not answer, so I could research on those topics. So it was a wonderful experience for me. Thank you.
And this is a certificate shared by Dr. Bablu Vishas. This is for Seona Jena, and let us congratulate her once again. And your cash award, as for Aditya Kishore also, it will be transferred to your account by some few days after. Okay. Thank you.
Sorry, I was muted. So thank you, Kaushikda, for the
No, it's
rest
okay.
part.
Okay. It's okay. No problem.
Okay. Next prize is Anita Bose Memorial Award, and it was won by Ayantika Basu. Ayantika, please keep your video on.
Yes, sir.
Many congratulations to you, and thank you for joining with us. And if you have any words, please share with us.
Yes, sir. It was a very wonderful experience. I got to learn a lot of new concepts, and the interview part, especially like questions were asked where I got to know where were the concepts I was lacking, and I got to research a lot about it. So it was a very knowledgeful experience. So, thank you.
Thank you very much. And I'm going to show your certificate. And sorry, this is not. So Antika, this is your certificate of achievement, and similarly, you will be awarded a 3,000 cash award, and will be sent to your account. Thank you for participating. Okay. Our last award is Sanjay Sen Memorial Award. It was owned by Sauraj Samaddar. Sauraj, please keep your video on. Are you here, Sauraj?
Yes, sir.
Very nice. Congratulations, Sauraj.
Yes, sir. Thank you, sir.
Sanjay Sen Memorial Award goes to you. And if you like to say something, please.
Yes, it was a very wonderful experience for me. Thank you very much for selecting me. I also learned many things through this valedictory session and interview session. Thank you so much.
Thank you. And I will also show your certificate. This is your certificate, and 3,000 cash award will be given also to you. And I will send this certificates within 1 or 2 days through your mail address. So thank you all 4 musketeers. I wish you every success in life for future, especially if you like mathematics. We will be very happy. Thank you.
Okay, thanks, Dr. Bablovicius. Thanks
Thank you.
for the presentation. I now invite Professor Molay Banerjee, convener of this conference, to do the summary of the conference.
Thank you, Manuel. So we have arrived towards the conclusion section of this international conference on recent developments in mathematics and mathematical sciences. It was spanned over last 3 days. It was started from 9th and going to end today within a couple of moments. So within this virtual platform and online conference, we had 8 invited talks. Among them, 5 were memorial lectures. Those are S.N. Bose Memorial Lecture, Police Memorial Lecture, Shuddhodhan Ghosh Memorial Lecture, Enar Sen Memorial Lecture, and Shaha Memorial Lectures. For all these 5 lectures and 3 more invited talks, we have experts from different parts of our globe. Sometimes what I can understand or what I can feel that this online virtual meeting gives us opportunity to have some person in our meeting who might not be able to spare some time to come to Calcutta and deliver the talk with offline mode, but they can spare a couple of hours for delivering talk in this particular event. So we made some sort of best effort from our side to make a balance between mathematics, which are completely theoretical, and some part which are applied. So that means once mathematical theory are developed or new results are coming up, then at the same time we need to understand where those results can be applied, or some application area also gives us opportunity to understand in which area we need to flourish or what other mathematical techniques is required to be developed further in order to strengthen multidisciplinary research. Because not only theory and formulas and several assumption is although it is a backbone of mathematics, but at the same time nowadays it is a hour of need to find a destination where such mathematical techniques can be applied. So apart from this invited talk, it is very overwhelming for us to see a huge number of submission for possible presentation in this virtual conference. Among them, we were able to select around 115 papers for the presentation, and this paper presentation was spanned over 3 parallel sessions during 4 time slots. One was on the first day, 2 slots was on 10th, and today we had 1 more session. So again, we have tried our level best to make a balance between presentation from different branches of mathematics, not inclined or some sort of bias towards any particular topic. Rather, we tried our level best to choose best submission, and also due to time constraint and some other technicalities, we were not able to invite all the submissions for presentation. So apart from this presentation, there is one more important part, that if you are interested to publish this presentation, so there will be 2 destinations. one is Bulletin of Calcutta Mathematical Society, and another one is Journal of Calcutta Mathematical Society. So notification will be circulated to all of you through email within couple of days. Anyway, it is very interesting and also important to mention that although this is a virtual mode, but mostly I must say more than 98 to 99% people have presented their talks, and also I have observed that people were actively present during most of the session, but due to the time constraint we were unable to have enough amount of discussion among us, or sometimes we did not allow participants to ask the question. But we hope that in near future we can meet together and this event can take place in offline mode once the pandemic is over, or we will have the opportunity to organize this kind of conference in offline mode. So I must thank the council body of Calcutta Mathematical Society to invite me to be a part of this program, although the entire exercise was carried out by Professor Arindam Bhattacharya, Dr. Bablu Bishwas, and my childhood friend Kaushik Ghosh. My presence was somehow ornamental, I must admit. I was not that much involved. The entire pain behind successful organization of this particular event is carried out by these three persons. And thank you each and every one who was involved in this particular conference, and hope to see you, most of you, in near future in offline mode during the future conferences that are going to take place in Calcutta Mathematical Society. Thank you very much.
Thank you, Professor Maulana Banerjee. Thank you for your nice things, what you have said. I will now ask for the feedback from the participants. It will be very nice to know what the participants believe and what they have thought about of this conference, and we will be very happy to know their feedback. So I am requesting the participant to give some feedback of this conference. Thank you. Well, if everybody keeps quiet, then it will be difficult. I think at least one or two persons should give some feedback. Hello.
Yes. May I ask Dr. Rajkumar? I think he was there very much in different sessions. If
Yeah, okay, fine.
Is he there?
Sure.
Dr. Raj?
Yeah, Rajkumar, I think I am seeing.
Rajkumar?
Yes, yes. Can you say some words, please?
Sir, I am Dr. Rajkumar from Tamil Nadu. I have seen most of the sessions of this conference. All the sessions are, we believe that, are very useful, and also it is helpful to develop the areas in which the researchers were encouraging that one. And about the contributions, we see that the timings and encouragements are all well, and moreover, we ask one thing that in the upcoming years, you may try the hybrid mode of online and offline. The online mode, I think it helps to the participants who are not reaching that directly. So we thank all of the organizers who had wonderfully organized this session. Thank you.
Thank you, Dr. Rajkumar. Thank you very much for your comments. I think one or two persons can also give.
Yeah. Can I ask Payal Kormokar? I think she's there.
No, I think she has given this thing. She
Uh,
has given it in words.
can you elaborate that one?
Yeah. Yeah, she said that thanks to all the organizers for this great conference, had a wonderful experience.
Hello, sir.
Well, any other? Yeah.
I'm Pal Karmakar from Jadavpur University. I would like to thank all the organizers. I had a very great experience in this conference. This was a wonderful platform for the researchers to share their work. Thank you very much. The talks were also very nice. Thank you.
Any other person, particularly, I will be happy to know from a person from the foreign country. Anybody, any person who can give some suggestions or some feedback. Well, Kaushik, there is a question coming up as well, whether the recorded version will be uploaded or not. Kaushik?
Yes.
Yes, yes, it will be uploaded and will be sent to the through mail. Okay.
Fine, fine.
It will be
Thank
shortly
you.
uploaded.
Link will be shared with all the participants and speakers.
Oh, good. Very nice. Thank you.
Yes.
So if there is no such suggestion, then feedback, then the next part is the suggestion from the council member of the Calcutta Mathematical Society. So these suggestions. I think council member should give one or two suggestions for this type of conference. Kaushik, I think you should start from your side first.
No, I think
Or
this is okay. I have said so many words. I have blabbered for all the 3 days. Better,
okay,
I
okay.
think, other
So Dr. Bablu
honorable members
wishes.
should say. Dr. Choktoraj is there. Professor Bera is there.
Right. Anybody, I think anybody can say.
Everything is all right. Only the link was posing some problem. And that was eliminated with no loss of time. And it is a great job for coordinating everything. And those involved deserve special thanks. Thanks to all.
Thank you. Any other person? Sir, Professor Rajkumar, actually, sir, you are there, sir. Sir, any suggestion from your side, sir? Our ex-president?
Professor Rajaudhuri, can you hear us?
I think sir is not there, I think. Okay, so I will request our our president, Professor Rashijit Vera, to say something on this, some sort of a suggestion.
I must congratulate the organizers, starting from secretary, then Dr. Kaushik, Dr. Bablu Vishwas, and everybody, and those who are not here, but outside the teaching staff, everybody is in the work for this conference to be successful, and they have done it a great job in this unusual circumstance and maintain their activity and energy for the coming years so that the Calcutta Mathematical Society can bear the burden of all the activity of the improvement of the society and the subject itself. So I thank you everybody for your wholehearted support to make the conference a great success.
Thank you, sir. Professor D.K. Ganguly, our ex-vice president, can you say something?
I think Sad is not present.
Okay. So Arindam, anything from your side, Dr. Arindam
I
Bhattacharya?
want to, yes, yes, I want to just mention and not mention that I want to thank Professor Maulay Banerjee, who is the main convener of this conference, for taking the responsibility of organizing such a great conference. And I also thank to our two pillars actually, Dr. Kaushik Ghosh and Dr. Bablu বিশ্বাস, those who are always taking the responsibility of conducting the parallel sessions and all uh, the sharing, who will chair or not, or the dividing the sessions. So many things they have very nicely uh, organized. So I also thank to our non-teaching staff of Calcutta Mathematical Society, those who have helped us in various ways. And another thing I want to mention that our memorial lectures, the 5 memorial lectures, there is a token honorarium for that, and we should seek the bank details of our memorial lecture who has given memorial lecture, and we will send the honorarium to the bank. Okay. So that much. And also for the advanced mathematical test also, Bablu and Kaushik has done a lot of work, and uh, all the 4 students will get same amount of prize money, and so there is no difference in that way. So with these words, I heartily congratulate to all for joining this international conference, and with a great success it has ending, hopefully. Okay, thank you.
Thank you.
Thank you.
Thank you, Dr. Arindam Bhattacharya. Thank you. So we appreciate the feedback given by the participant. The feedback will be our yardstick for the next year conference. We are delighted to hand over the prizes to our little mathematician, who we believe will excel in mathematics in near future. Who knows? One day they will become another Nikhil Srivastava, solving some unsolved problem and bring laurel to the country. We all wish them a great success in their life. Before I hand over my digital mode to Dr. Bablu Bishas for a final vote of thanks, may I request all the participants, it is just my request, to become a life member of our society, to make our society enrich with thoughts and ideas. You can get the life membership of our society in our website. So now I hand over my digital mode to Dr. Bablu Bishas for a final vote of thanks.
So thank you. So we are at the fragment of this conference. It is a long way, I think. So it's my privilege to have the opportunity to propose the vote of thanks in this international conference on recent development in mathematics and mathematical sciences. On behalf of the organizing committee, I thank all the stakeholders who have contributed to organize and execute this conference successfully. I convey my deep regards and thanks to our Honorable President Sir, Professor Rosojit Bera, and all the Vice Presidents, Professor Joydev Chattopadhyay, Professor Tanmay Shom, Professor Kajol De, Professor Sanjeev Kumar Dotto, Professor Devidas Chattoraj, for their motivation, inspiration for this and for this conference. I have no enough words to thank our respected Secretary, Professor Arindam Bhattacharya, for his continuous help in every aspect and dedicated and I think dynamic leadership. I also thank our Assistant Secretary, Dr. Partha Karmakar, for his efforts. I must mention my deep sense of appreciation to all our council members for their supports and extending helping hands in all possible manners. I have mentioned especially the I want to mention especially the name of our ex Vice President Professor Rajkumar Roy Chaudhary and ex Vice President Professor Dilip Kumar Ganguly for their valuable suggestions. And I think they are always kind enough to help us in every problem. So thank you, sir. I may like to express my sincere thanks and appreciation to all our elegant speakers who illuminated us the way to have proper and interesting ideas about the advanced concept of mathematics. I would like to thank the chairpersons of all the chairpersons for conducting the session efficiently, and most importantly, I heartily thank our excellent participants for joining the conference and presenting their nice works here. And one thing I should not forget that to thank Principal P.N. Das College for providing the technical help for this 3-day conference. And really, there is no enough words to thank Professor Malay Banerjee, joint convener of this conference, and Dr. Oshik Ghosh, coordinator of this conference. During the last 3 days, they are available almost 24 hours to moderate, to rectify, to modify, and to manage all the problem and issues related to this conference. In this tremendous task, it may not be possible to make every person happy, but we honestly have tried hard, and thank you everyone once again. Thank you all. Thank you. And one thing I should mention that for the participants, the feedback link will be sent to you within, I think it will be tomorrow, through your email. And I would like to request all the participants, please kindly fill all the required items in that form carefully, because on that information will make certificates for you, and please be careful when you are filling that form. Thank you. It's all
Thank
from
you,
me.
Dr. Shash. So finally, I say that the conference ends here. And bye, everybody. Hope you will be enjoying your life and be careful about the pandemic situation. Thank you. Thank you very much.
Thank you, Dr. Banerjee. Thank you, everyone, and stay safe. Bye-bye. Thank you.
Good night.
Good night, everyone.
Okay, good night. We'll meet afterwards.
Thank you, sir.
Bye. Bye.
Thank you.
Bye, everyone. Thank you.
Yeah, bye.